before. And then Webb found something even more unexpected buried inside that same glowing coma: methane. Plain, simple methane, the same molecule that powers stoves on Earth and drifts in the atmospheres of gas giants, detected drifting off the surface of an object that has been in the deep freeze of interstellar space for longer than our entire solar system has existed. Methane is fragile. It breaks down fast under sunlight and cosmic radiation. Finding it intact, still venting off this ancient wanderer after a 10-billion-year journey, tells scientists that whatever formed 3I/Atlas locked that methane away somewhere so cold, so shielded, so untouched, that it survived a trip longer than the age of Earth itself. To catch methane at all, Webb had to use one of its most sensitive instruments, the MIRI spectrometer, tuned to mid-infrared wavelengths that ground-based telescopes simply cannot see through Earth's atmosphere. No observatory on the ground could have made this detection. It took a telescope parked nearly 1,000,000 miles from Earth, cooled to almost absolute zero, sensitive enough to read the faint chemical whisper coming off an object racing away from the sun at incredible speed. This is precisely the kind of measurement Webb was built for, not just pretty pictures of distant galaxies, but forensic chemistry performed on objects too faint and too fast for anything else humanity has ever built. But the detection that really turned heads was right now, as you are reading these words, as you are breathing, as the Earth turns silently beneath your feet at 1,000 miles per hour, something is falling toward you. Not a meteor, not a comet, not some ancient rock from the outer edges of the solar system that wandered too close. Something we built, something we launched, something that spent 14 years doing arguably the most important scientific work any spacecraft has ever done in near-Earth space. And now, its job complete, its fuel exhausted, its batteries slowly dying in the cold vacuum beyond the atmosphere, it is coming home. Its name is Van Allen Probe A. It weighs approximately 600 kilograms. That's roughly the weight of a full-grown brown bear, or a vintage Harley-Davidson motorcycle, or about 4.5 washing machines bolted together and hurtling through the upper atmosphere at 17,000 miles per hour. And somewhere over the next several hours, it is going to hit the atmosphere. Let that land for a moment. We are not talking about some abstract astronomical event that happens millions of light years away, something you need a telescope to appreciate. We are talking about a piece of American engineering, designed by American scientists, built by American hands, paid for by American taxpayers, launched from American soil, completing its final arc and returning in the most dramatic fashion imaginable to the planet that sent it skyward. This is the story of Van Allen Probe A, and it is one of the most fascinating stories in the history of American space science. But to understand why this moment matters, why this particular piece of hardware deserves more than a footnote in tomorrow's news cycle, you have to go back. You have to go back to the beginning of the space age, to a time when humanity first dared to look beyond the thin shell of air that protects us from the lethal fury of the cosmos. You have to go back to a discovery so surprising, so fundamentally important, so completely unexpected that it changed everything we thought we knew about our own backyard in space. You have to go back to 1958. January 31st, 1958. The United States is in a state of barely contained panic. 4 months earlier, on October 4th, 1957, the Soviet Union had launched Sputnik, a 184-pound metal sphere about the size of a beach ball, into orbit around the Earth. The beeps it transmitted back to Earth were picked up by ham radio operators across America, and those beeps hit the American psyche like a psychological thermonuclear device. The Soviets were in space. The Soviets were orbiting the Earth. The Soviets, who had tested their first nuclear bomb less than a decade earlier, who had built an intercontinental ballistic missile capable of delivering a nuclear warhead to American soil, had now demonstrated that they could put hardware into orbit, which meant, by extension, that they could put nuclear warheads into orbit. America's response was the kind of frantic, urgent, borderline chaotic mobilization that only happens when a nation feels genuinely threatened. The Naval Research Laboratory had been working on a satellite project called Vanguard. But Vanguard was moving slowly, carefully, methodically, the way good engineering moves when it isn't being rushed by geopolitical terror. Then Sputnik flew, and suddenly Vanguard was the most important project in America. And then, on December 6, 1957, in front of a live television audience, Vanguard's rocket rose about 4 feet off the launch pad and exploded. The satellite, a tiny 3-pound sphere, was thrown clear of the explosion, still transmitting, lying in the burning wreckage at the base of the launch pad. The press called it Flopnik. The humiliation was complete. America needed a win, and America needed it fast. The Army Ballistic Missile Agency, led by Wernher von Braun, a complicated man with a complicated history who had built rockets for Nazi Germany and was now building them for the United States, had a rocket ready. The Jupiter C. They had wanted to launch a satellite since 1956 and had been told to wait while Vanguard took its shot. Now, with Vanguard burning on the launch pad, they were given the green light. They had 90 days to do it. They did it in '84. On January 31st, 1958, Explorer 1 lifted off from Cape Canaveral, Florida, and became the first American satellite in orbit. The scientists, engineers, and technicians who had built it, many of them barely sleeping, running on coffee and adrenaline and the particular kind of focus mania that descends on people who know that history is watching, stood in a room in Washington and waited. And waited. The satellite was supposed to make contact at a specific time when its orbit brought it over receiving stations. The time came. Nothing. The time passed. Still nothing. The room was silent in the particular way that rooms get silent when everyone in them is trying to hold on to hope with their fingernails. And then, 25 minutes late, the signal came through. Explorer 1 was in orbit. The first American satellite was in space. The men in that room embraced and wept and held each other up. But something was wrong. Not with the satellite. The satellite was fine. The problem was with the data. Explorer 1 carried a Geiger counter, a device designed to measure cosmic radiation. The scientist responsible for that instrument was a man named James Van Allen, a physicist from the University of Iowa who had spent years studying cosmic rays by attaching instruments to high-altitude balloons and rockets. He had been arguing for years that the United States needed to study the radiation environment near Earth from orbit, and he had finally gotten his chance. The Geiger counter worked. It transmitted data back to Earth. But the data was strange. At certain altitudes and certain positions in the orbit, the radiation readings went through the roof. And then, at other points, the Geiger counter went completely silent. Not low readings. 0 readings. As if there was nothing there at all. Van Allen and his team puzzled over this. A Geiger counter doesn't just stop working. If there's nothing there, it reads nothing. But if there's something there, a lot of something, if the radiation intensity is so high that it saturates the detector and overwhelms its ability to count individual particles, the counter goes to 0. The silence wasn't absence. The silence was an overload. Van Allen ran the math. He ran it again. He ran it a third time and then called in his colleagues to run it with fresh eyes. The conclusion was inescapable. Surrounding the Earth, at altitudes ranging from roughly 1,000 kilometers to tens of thousands of kilometers above the surface, there were zones of intense, trapped radiation. Belts of high-energy charged particles, electrons and protons, trapped by the Earth's magnetic field, spiraling back and forth from pole to pole, bouncing like cosmic pinballs in a vast invisible cage made of magnetism. No one had predicted this. No one had imagined it. The textbooks did not contain these zones. They did not exist in any theoretical framework that anyone had developed before Explorer 1 flew. They were real. They were massive. They were everywhere in a cosmic sense. And they were entirely unknown until a physicist from Iowa, working with a satellite that almost didn't get launched, discovered them by accident. We named them after him. The Van Allen radiation belts. The Van Allen radiation belts are, by any measure, one of the most extraordinary features of our immediate cosmic neighborhood, and one of the least appreciated. Ask the average person what lies between the surface of the Earth and the Moon, and they will probably say space. Just space. Empty, dark, cold space. They're not entirely wrong, but they're missing something crucial. What actually lies between you and the Moon is a seething, dynamic, constantly shifting environment of charged particles and magnetic fields that is as complex and as violent, in its own way, as anything you'll find anywhere else in the solar system. It is a place where electrons travel at close to the speed of light, where protons carry enough energy to penetrate the walls of a spacecraft, where the radiation levels in the heart of the belts are high enough to kill an unshielded human being in a matter of minutes and damage sophisticated electronics in hours. It is, in the very technical language of space science, a seriously hostile place. And yet it's right here. It's not around Jupiter or Saturn. It's not in some distant region of the galaxy. It's right above our heads, starting at about 1,000 kilometers altitude and extending out to about 60,000 kilometers, well past the orbit of the Moon in terms of the inner edge of the magnetosphere's influence. The inner Van Allen belt is the more stable of the two. It sits roughly between 1,000 and 5,000 kilometers above the surface and is dominated by high-energy protons, the bare nuclei of hydrogen atoms, stripped of their electrons, moving at tremendous speed. These protons get there primarily through a process called cosmic ray albedo neutron decay, or CRAND, which is one of those phrases that sounds made up but is very real and very physics. Cosmic rays hit the upper atmosphere, produce neutrons, those neutrons decay into protons, and some of those protons get trapped in the magnetic field. It's a slow, steady process that has been building up the inner belt for as long as the Earth has had a magnetic field. The outer belt is different. It's larger, it extends from about 12,000 to 60,000 kilometers, and it is dominated by electrons, the fast, light, negatively charged particles that are the opposite number to protons. The outer belt is far more dynamic than the inner one. It changes dramatically in response to solar activity. During a strong solar storm, the outer belt can swell and intensify dramatically, flooding the region with high-energy electrons that can charge up spacecraft, damage solar panels, and destroy electronics. During quiet periods, it can shrink and become relatively benign. And between the two belts, there is a gap, a slot region, relatively free of intense radiation, where the two belts don't quite overlap. This slot region is maintained by electromagnetic waves in the atmosphere that continuously scatter electrons back into the atmosphere before they can build up. Or so scientists thought before the Van Allen probes showed them just how wrong they were. James Van Allen's discovery in 1958 set off decades of research. Dozens of spacecraft were sent to study the belts. Data accumulated. Models were built. By the late 1990s and early 2000s, scientists believed they had a reasonably good understanding of how the Van Allen belts worked. They had an outline. They had a rough sketch. But they were missing enormous pieces of the picture, and some of what they thought they knew turned out to be wrong. The problem was instrumentation. The satellites that had studied the Van Allen belts over the decades were, by the standards of modern space science, relatively crude instruments. They could detect the presence of radiation. They could measure general energy levels. But they couldn't see the fine structure of what was happening. Couldn't watch individual populations of particles as they moved and bounced and were energized and were lost. Couldn't measure the electric and magnetic fields with the precision needed to understand the wave-particle interactions that drive the belt's behavior. Couldn't watch the belts respond to a solar storm in real time with enough detail to actually understand the mechanisms at work. It was like trying to understand the human circulatory system using only a stethoscope. You can hear that something is happening. You can get a rough sense of rate and rhythm, but you can't see the blood cells, can't watch the valves open and close, can't understand the biochemistry of what's flowing through those vessels. To really understand the Van Allen belts, you needed better instruments. You needed instruments that could measure the energy spectrum of trapped particles with high resolution, that could detect the plasma waves that interact with those particles and either accelerate them or cause them to fall into the atmosphere, that could measure the electric and magnetic fields with exquisite precision, that could capture the detailed structure of the radiation environment as the spacecraft moved through it. And you needed to do all of this not from a single spacecraft but from two spacecraft flying together, so you could distinguish between changes that were happening in time from changes that were happening in space, because those are two completely different things, and you can't tell them apart from a single point of measurement. This was the scientific case for what eventually became the Van Allen probe's mission. And it was a compelling case, so compelling that NASA approved it, funded it, and sent it through the long, complicated, expensive, demanding process of turning a scientific vision into a working spacecraft. The mission that would become the Van Allen probes was originally conceived in the early 2000s under the name RBSP, Radiation Belt Storm Probes. The name was accurate but unglamorous, the kind of label that makes perfect sense to a scientist and means absolutely nothing to anyone else. When the spacecraft were finally ready to launch in 2012, NASA renamed the mission the Van Allen probes, a fitting tribute to the man whose accidental discovery had defined the scientific question they were trying to answer. The two spacecraft, Van Allen Probe A and Van Allen Probe B, were built by the Johns Hopkins University Applied Physics Laboratory, or APL, in Laurel, Maryland. APL has a long history of building spacecraft for NASA and the Department of Defense, and they brought that experience to bear on a mission that presented some genuinely difficult engineering challenges. The most fundamental challenge was the radiation environment itself. You want to build spacecraft to study the Van Allen belts. The Van Allen belts are the most radiation-intense environment in near-Earth space. To build spacecraft that can survive in the Van Allen belts long enough to study them, you have to protect them from the very radiation they're going to spend their lives measuring. This is not a trivial problem. High-energy electrons can penetrate spacecraft walls and build up charge on insulating surfaces, then discharge suddenly in what's called an electrostatic discharge event, essentially a miniature lightning bolt inside your spacecraft. High-energy protons can damage solar cells, degrading the spacecraft's power generation over time. Both electrons and protons can scramble the memory in electronic components, causing what are called single-event upsets, random bit flips that can corrupt data or cause computers to execute incorrect instructions. APL engineers spent years designing radiation-hardened electronics and developing shielding schemes that would protect the most sensitive components without adding so much mass that the spacecraft became too heavy to launch. They ran computer simulations of the radiation environment and calculated how much shielding was needed to keep total radiation doses within acceptable limits over the planned mission life of 2 years. They tested components in particle accelerators, deliberately exposing them to high-energy radiation to see how they would degrade over time. The result was two nearly identical spacecraft, each about the size and shape of a large octagonal hatbox. Or, if you prefer, imagine a piece of carry-on luggage that's been sat on by something very heavy and spread out into a flat octagon. Each spacecraft was approximately 1.8 meters across and about 1.2 meters tall. Each weighed about 600 kilograms, more than half a metric ton, including fuel. 5 science instrument suites were mounted on each spacecraft, giving the mission a comprehensive ability to measure every aspect of the radiation belt environment. The Electric and Magnetic Field Instrument Suite and Integrated Science, or EMPhaSIS, measured the magnetic and electric fields and the plasma waves that interact with trapped particles. The Electric Field and Waves Instrument, or EFW, measured the electric field using 4 50-meter wire booms that deployed from the spacecraft like mechanical spider legs, extending out to measure the electric field across a span wider than a football field. The Energetic Particle, Composition, and Thermal Plasma Suite, or ECT, measured the population of trapped particles across a wide range of energies. The Relativistic Proton Spectrometer, or RPS, measured the highest energy protons in the inner belt. And the Radiation Belt Storm Probe's Ion Composition Experiment, or RBSPICE, measured the composition and energy of ions, the heavier positively charged particles that help drive the dynamics of the ring current, a giant toroidal current that flows around the Earth and is closely related to the Van Allen belts. This instrument package was comprehensive enough to capture essentially every important aspect of the radiation belt environment. The two spacecraft would fly in slightly different orbits, so they would sample different parts of the belt at the same time, allowing scientists to separate spatial from temporal variations. Over the course of the mission, the orbits would process slowly rotate so that the spacecraft would gradually sample every local time at every altitude, building up a complete three-dimensional picture of the belt environment. It was an elegant scientific design. It was also, practically speaking, a monumental engineering achievement. August 30th, 2012. The Atlas V rocket stands on its launch pad at Cape Canaveral Air Force Station, its white body gleaming in the Florida humidity, the Van Allen probes nestled inside its payload fairing. It is 4:05 in the morning, local time, and the beach near the launch site is lined with people who have come to watch, space enthusiasts, families of mission team members, photographers with enormous telephoto lenses pointed at the distant flame of the rocket's engines. The countdown reaches 0. The Atlas V ignites. Its main engine and solid rocket boosters produce approximately 1.7 million pounds of thrust, and the rocket lifts off in a pillar of fire and smoke that lights up the pre-dawn darkness like a second sunrise. Spectators on the beach shield their eyes and feel the rumble in their chests. The rocket accelerates through the thick lower atmosphere, climbing, tilting, beginning its arc over the Atlantic. About 4 minutes after launch, the payload fairing, the aerodynamic nose cone that protects the spacecraft during ascent through the atmosphere, separates and falls away. Above the densest part of the atmosphere, the spacecraft no longer need protection from the wind. They are exposed to space for the first time. The Centaur upper stage fires, boosting the stack into an intermediate parking orbit. It fires again, pushing toward the final target orbit, a highly elliptical path that takes the spacecraft from a perigee of about 600 kilometers altitude at its closest point to Earth all the way out to 30,600 kilometers at its farthest point. This orbit is designed to take the spacecraft through the heart of both Van Allen belts on every pass. In and out, up and down, sweeping through the radiation environment twice on every single orbit, which takes about 9 hours to complete. The spacecraft separate from the Centaur, first Probe B and then Probe A. They extend their wire booms and antennas. They power up their instruments. They begin talking to the ground. They are in the Van Allen belts. They are measuring. The mission has begun. The science that came back over the following years was nothing short of extraordinary. Let's start with what might be the single most dramatic discovery the Van Allen probes made: the existence of a third radiation belt. For 54 years after Van Allen's original discovery, scientists had understood that there were two Van Allen belts, the inner belt and the outer belt, with a relatively empty slot region between them. This was textbook knowledge. It was in every space physics textbook. It was the foundational understanding of the near-Earth radiation environment. It was wrong, or rather, it was incomplete. In September 2012, just weeks after the Van Allen probes launched, a powerful solar storm hit the Earth. Solar storms, also called geomagnetic storms, happen when the sun ejects a massive cloud of magnetized plasma called a coronal mass ejection, or CME, and that CME hits the Earth's magnetosphere. When a big CME arrives, it can compress and distort the magnetosphere, dramatically intensifying the Van Allen belts and sometimes injecting new particles into them. Scientists had seen this happen before. Solar storms intensify the outer Van Allen belt. Standard behavior, textbook stuff. But then something unexpected happened. The electrons that had been injected by the solar storm, a massive population of high-energy particles sitting in the outer belt, began to respond to the changing electromagnetic environment in a way no one had anticipated. Instead of the simple two-belt structure reforming as the storm subsided, the data from the Van Allen probes showed the formation of a distinct third belt, a new, separate band of high-energy electrons sitting in the slot region between the inner and outer belts. This third belt persisted for 4 weeks before finally being wiped out by another solar event. But those 4 weeks were enough to upend decades of theoretical understanding and force scientists to completely rethink their models of how the belts work. How does a third belt form? What maintains it? Why does it appear in the slot region, which electromagnetic wave interactions are supposed to keep clear? The answers to these questions turned out to involve a complex interplay of different types of waves and particle populations that was far more subtle than anyone had previously suspected. The discovery of the third belt was published in Science magazine in February 2013, just 6 months after launch, and it sent shockwaves through the space physics community. It was one of those moments in science where a result is so clean, so unambiguous, so clearly important, that even the most skeptical observer has to sit down and rethink their assumptions. But the third belt was just the beginning. One of the deepest mysteries in Van Allen belt physics is the question of particle acceleration. How do the electrons in the outer belt get to be so energetic? Electrons in the outer Van Allen belt can reach energies of millions of electron volts, energies so high that they travel at more than 90% of the speed of light. At those speeds, relativistic effects become important. These particles are so fast that Einstein's special relativity actually matters for calculating their behavior. Scientists call them killer electrons because of their ability to penetrate and damage spacecraft electronics. How do electrons get that energetic? Where does the energy come from? Before the Van Allen probes, there were two main competing theories. The first theory was called radial diffusion. The idea here is that electrons start out at high altitude, where the magnetic field is relatively weak, and slowly diffuse inward toward lower altitudes where the field is stronger. As they move inward, the magnetic field does work on them, squeezing them and accelerating them, in the same way that a spinning ice skater speeds up when they pull their arms inward. Radial diffusion is driven by large-scale fluctuations in the electric and magnetic fields, fluctuations caused by solar wind pressure variations and other large-scale disturbances. The second theory was local acceleration. The idea here is that electrons get accelerated in place, right where they are in the outer belt by interactions with plasma waves. Specifically, a type of wave called chorus waves, electromagnetic Whistler mode waves generated by lower-energy electrons in the outer magnetosphere, can transfer their energy to trapped electrons through a process called cyclotron resonance. If a chorus wave oscillates at exactly the right frequency to match the natural orbital motion of an electron around a magnetic field line, the two can exchange energy very efficiently, and the electron can gain a tremendous amount of energy in a relatively short time. Both processes are real. Both happen. The question was, which one is dominant? Which one is primarily responsible for creating the most energetic electrons in the outer belt? The Van Allen probes answered this question definitively. By measuring both the particle populations and the wave environment simultaneously, with unprecedented precision, the mission scientists were able to watch local acceleration in action. They could see chorus waves of exactly the right frequency building up in the outer magnetosphere. They could see populations of lower-energy electrons, what scientists call seed electrons, available to be accelerated. They could see the higher-energy electron population growing over time, exactly in the regions where the wave activity was strongest. The evidence for local acceleration was overwhelming. Radial diffusion contributes to the outer belt's energization, but the primary mechanism, the engine that takes seed electrons and pushes them up to relativistic energies, is local acceleration by chorus waves. This finding has profound implications for our ability to predict and forecast space weather. If you want to know how dangerous the outer Van Allen belt is going to be for a spacecraft tomorrow or next week, you need to know where the chorus waves are and how intense they are, not just the large-scale state of the magnetosphere. This means that the input to space weather models has to include wave activity, a variable that had previously been very difficult to measure and that most models had simply neglected. Space weather. Let's pause here because this concept is central to understanding why the Van Allen probe's mission was funded, why it matters, and why the discoveries it made have implications that extend far beyond academic space physics. You've heard of weather forecasting. You understand that the atmosphere is a dynamic system driven by the sun's energy, with currents and fronts and pressure systems that create the winds and rains and storms that affect daily life. Modern meteorology has become remarkably good at predicting the atmosphere's behavior. Not perfectly, because the atmosphere is a chaotic system, but well enough that a 5-day forecast is now roughly as accurate as a 1-day forecast was 30 years ago. Space weather is the analogous concept applied to near-Earth space. The sun is constantly emitting a stream of charged particles called the solar wind, a tenuous plasma of electrons and protons flowing outward from the sun at speeds ranging from about 300 to 800 kilometers per second. This solar wind carries with it the sun's magnetic field, twisted into a complex, dynamic structure by the sun's rotation and convection. When the solar wind interacts with the Earth's magnetic field, the magnetosphere, it creates a complex, dynamic system of currents and fields and particle populations. Under quiet conditions, this interaction is relatively benign. But the sun is not always quiet. The sun has an 11-year activity cycle, and during the active part of the cycle, solar maximum, it produces frequent solar flares and coronal mass ejections that dramatically perturb the near-Earth environment. A big geomagnetic storm can enhance the Van Allen belts dramatically, filling the near-Earth environment with high-energy electrons that can damage or destroy satellites. The 1989 geomagnetic storm caused by a powerful CME knocked out an entire Hydro-Quebec power transformer, leaving 6 million people without electricity for up to 9 hours. The same storm permanently degraded the solar panels on several satellites. A particularly powerful electron enhancement event in 2003, during the Halloween storms, damaged or destroyed at least 2 commercial satellites and caused the loss of approximately $450 million in spacecraft hardware. Some estimates put the damage across multiple spacecraft at over $1 billion. Interfere with GPS signals. The ionosphere, the upper layer of the atmosphere, above about 80 kilometers altitude, is filled with charged particles that affect the propagation of radio waves. During geomagnetic storms, the ionosphere becomes turbulent and variable, causing GPS signals to scatter and introduce errors. For civilian navigation, this is an inconvenience. For precision agriculture, surveying, and certain military applications that depend on centimeter-level GPS accuracy, it can be a serious operational problem. Induced currents in long conductors at the surface. The changing magnetic fields during a geomagnetic storm can induce electric currents in power lines, pipelines, and railroad tracks. These geomagnetically induced currents, or GICs, can damage or destroy transformers, the expensive, difficult-to-replace equipment that forms the backbone of the power grid. A Carrington-scale event, comparable to the geomagnetic storm of 1859, which by some estimates was the most powerful geomagnetic storm in recorded history, could potentially knock out electrical power to large parts of North America for weeks or months. The economic impact has been estimated in the trillions of dollars. Expose airline passengers and crew to elevated radiation. During solar energetic particle events, the radiation dose rates at high altitude and high latitude can increase dramatically. Aviation regulators and airlines monitor space weather forecasts to decide whether to divert flights away from polar routes during major events. This is not hypothetical. This is not science fiction. These are real, documented, economically significant impacts that space weather has on modern technological society. And they are becoming more significant as society becomes more dependent on the satellite infrastructure that sits squarely in the radiation belt environment. The Van Allen probes were designed to improve our ability to understand and predict these events. Every discovery they made about how the belts are energized, about what drives loss and intensification, about the role of wave-particle interactions, translates directly into better models, better forecasts, and ultimately better protection for the systems that modern civilization depends on. Let's talk about loss. We've talked about how electrons get into the outer Van Allen belt and how they get energized. But the outer belt is not a simple trap. Electrons don't just accumulate there indefinitely. They're constantly being lost, and understanding loss processes is just as important as understanding acceleration. Electrons can be lost from the Van Allen belts in several ways. They can be scattered into the loss cone. The range of pitch angles at which their helical motion along a magnetic field line will carry them into the dense atmosphere at the ends of the field line, where they collide with atmospheric molecules and are absorbed. Wave-particle interactions can scatter electrons into the loss cone, essentially kicking them out of the trap. Chorus waves, which we already mentioned as an important acceleration mechanism, can also scatter electrons into the loss cone and cause them to be lost. Electromagnetic ion cyclotron waves, EMIC waves, are particularly effective at scattering the most energetic electrons, the ones with energies above a few MeV, and causing them to precipitate into the atmosphere. They can be transported outward, pushed to higher altitudes by electromagnetic perturbations, and then carried away by the solar wind into the outer magnetosphere, where the trapping is less effective and they eventually escape. They can be lost to spacecraft themselves. Every satellite in the radiation belt environment is constantly absorbing a tiny fraction of the electron population, though this is a negligible effect on the total belt population. One of the key findings of the Van Allen probes was the discovery of a sharp, remarkably stable boundary at the inner edge of the outer electron belt, a precise altitude below which relativistic electrons essentially cannot penetrate, even during the most powerful geomagnetic storms. This boundary sits at a distance of about 2.8 Earth radii from the center of the planet, about 11,000 kilometers above the surface. During storm after storm, scientists watched high-energy electrons piling up against this boundary, intensifying just outside it, but never crossing it. They called it the impenetrable barrier. What creates this barrier? After careful analysis, the Van Allen probes team concluded that the barrier is maintained by very low-frequency radio waves, electromagnetic waves in the VLF range, generated by lightning in Earth's atmosphere and by human-made transmitters, including power lines and military communication systems. These waves propagate out into the inner magnetosphere and interact with the relativistic electrons, scattering them into the loss cone before they can penetrate below the barrier. In other words, the very same electromagnetic noise that our civilization generates. Our power lines, our radio transmitters, the lightning that crackles in thunderstorms over every ocean and continent, is constantly working to keep the most dangerous radiation away from us. There is an electromagnetic shield around the Earth, and it is partially maintained by the electromagnetic signature of human activity. That is extraordinary. That is the kind of finding that makes you stop and think about the invisible ways in which the Earth's environment and human civilization interact. We are, without knowing it or intending it, contributing to our own protection from cosmic radiation. Let's talk about the slot region. Between the inner and outer Van Allen belts lies the slot region, a band of relatively low radiation that sits roughly between 2 and 3 Earth radii from the planet's center, corresponding to altitudes of roughly 8,000 to 12,000 kilometers. This is one of the most valuable orbits in cislunar space because it's far enough from Earth to have global coverage, yet low enough to avoid most of the intense radiation of the outer belt. Many important satellites, including GPS satellites, which orbit at about 2.6 Earth radii, occupy this region. Keeping it relatively radiation-free is economically and strategically significant. Before the Van Allen probes, scientists understood that the slot region is kept clear by plasmaspheric hiss, a type of electromagnetic wave that propagates through the dense, cold plasma of the plasmasphere, the inner region of the magnetosphere. Plasmaspheric hiss efficiently scatters electrons into the loss cone, preventing them from accumulating in the slot region. But the Van Allen probes revealed that this picture was significantly more complicated than anyone had realized. They discovered that the structure and behavior of the slot region depends critically on the energy of the electrons involved. Very high-energy electrons, the most damaging ones for spacecraft, can penetrate deeply into the slot region during powerful storms, in ways that older models had not predicted. The precise depth of penetration depends on the amplitude and frequency of the hiss waves, which in turn depends on the density of the plasmasphere, which changes dramatically during geomagnetic storms. The plasmasphere itself turned out to be far more dynamic than previously thought. The Van Allen probes, equipped with a Langmuir probe that could measure the local electron density, watched the plasmasphere expand and contract in response to geomagnetic activity, bulging outward during quiet times and then being eroded away by the solar wind during storms, shrinking back toward Earth as the outer layers of cold plasma were stripped away. When the plasmasphere contracts, it takes the hiss waves with it. The slot region, no longer bathed in the hiss that was maintaining it, becomes vulnerable to electron injection. The electrons rush in, and for a brief time, the slot region is no longer a slot. Then the storm subsides. The plasmasphere begins to refill, slowly rebuilding from the warm plasma that drifts up from the ionosphere. The hiss returns. And gradually, over days to weeks, the electrons that had invaded the slot region are scattered back into the atmosphere, and the slot is restored. This dynamical picture, the slot region as something that is continuously maintained by wave activity, constantly under assault during storms, capable of briefly disappearing and then slowly reforming, is dramatically richer than what scientists believed before the Van Allen probes flew. Now I want to tell you about ring currents because the ring current is one of the most important features of the near-Earth space environment and one of the features that the Van Allen probes helped illuminate most powerfully. The ring current is a vast donut-shaped current of charged particles flowing westward around the Earth at distances of roughly 2 to 9 Earth radii from the center of the planet. It flows primarily through the motion of ions, protons, and heavier ions like oxygen and helium, trapped in the inner magnetosphere and drifting around the Earth under the combined influence of the magnetic field's gradient and curvature. The ring current is important for several reasons. First, it produces its own magnetic field. Like any electric current, the ring current is surrounded by a magnetic field, and this field is oriented to partially oppose the Earth's own magnetic field at the surface. When the ring current intensifies during a geomagnetic storm, the magnetic field at the surface of the Earth decreases measurably. This decrease is what the DST index, the Disturbance Storm Time Index, measures, and it's the primary metric that scientists use to quantify the severity of geomagnetic storms. A very severe storm might produce a DST decrease of -300 nanotesla or more, a measurable weakening of the Earth's magnetic field over the entire planet. Second, the ring current carries a lot of energy. The total energy stored in the ring current during a major geomagnetic storm can reach 10 to the power of 16 joules, roughly equivalent to a few years' worth of global electrical power consumption, concentrated in a plasma structure the size of a small planet. Third, the ring current interacts with the Van Allen belts in complex ways. Energetic neutral atoms, particles that result when ring current ions exchange charge with cold neutral hydrogen atoms in the upper atmosphere, carry information about the ring current's composition and energy that can be detected from a distance. Wave modes generated by the ring current can interact with radiation belt electrons and affect their behavior. Before the Van Allen probes, the ring current was known to exist and its gross properties were understood, but its detailed dynamics, especially the role of different ion species and the mechanisms of ring current loss, were poorly characterized. The reshape instrument on the Van Allen probes was specifically designed to address this gap. It measured the flux and composition of ions across a wide energy range, from thermal energies up to several hundred keV. Over the course of the mission, it built up a detailed picture of how the ring current is injected, how it evolves during storms, and how different ion species contribute to the total current. One of the key findings from reshape was the importance of oxygen ions in the ring current. During major geomagnetic storms, the ring current is dominated not by protons but by oxygen ions, atoms from the Earth's upper atmosphere that have been stripped of their electrons and injected into the magnetosphere during intense storms. This means that the ring current is not just a feature of the solar-wind interaction with the magnetosphere but is fed, in part, by the Earth's own atmosphere. The Earth, it turns out, is not a passive recipient of the solar wind's energy during geomagnetic storms. It is an active contributor, feeding its own atmosphere into the ring current and reshaping the near-Earth environment in response to solar activity. I want to take a step back and ask a question that might seem simple but actually leads somewhere profound. Why does the Earth have a magnetic field at all? The Earth's magnetic field is generated deep inside the planet, in the outer core, a layer of molten iron and nickel extending from about 2,900 to 5,100 kilometers below the surface. This liquid metal is in constant motion, driven by the heat of the inner core below it and by the Coriolis effect of the Earth's rotation. The motion of this electrically conducting fluid generates electric currents, and those currents generate the magnetic field. This process, the generation and maintenance of a planetary magnetic field by the motion of a conducting fluid, is called a geodynamo. It's one of the most complex physical processes on Earth, governed by the same equations that describe magnetic fields and fluid dynamics, equations that remain impossible to solve analytically for realistic configurations and that even supercomputer simulations can only approximate. The Earth's magnetic field is not static. It varies in strength and direction over time. Over the course of decades and centuries, the magnetic poles wander. The North Magnetic Pole has moved thousands of kilometers over the past century, recently accelerating its motion toward Siberia. Over the course of hundreds of thousands to millions of years, the field reverses completely. North becomes south, south becomes north. The geologic record shows that the Earth has undergone more than 170 polarity reversals in the past 100 million years, each reversal taking roughly 1,000 to 10,000 years to complete and being marked by a period of reduced field strength and complex, multipolar field structure. The last full reversal happened about 780,000 years ago. We may be in the early stages of another. The field has weakened by about 9% since the early 19th century, though it's unclear whether this is the beginning of a reversal or just a temporary fluctuation. Why does this matter for the Van Allen belts? Because the Van Allen belts exist because of the magnetic field. No magnetic field, no belts. A weakened magnetic field means a reduced ability to trap particles, a different belt structure, and potentially a much more radiation-intense environment at lower altitudes than we're accustomed to. During a polarity reversal, when the field is at its weakest and most complex, the radiation environment in near-Earth space would be profoundly different from what we see today. There might not be well-defined Van Allen belts at all. The surface radiation environment might be significantly higher. The implications for any life forms or civilizations that happen to exist during such a period are uncertain but potentially significant. The Van Allen probes didn't directly study the geodynamo. That's not what they were built for. But their work on the relationship between the magnetic field structure and the radiation belt environment deepens our understanding of how intimately connected these two things are, and why the long-term evolution of the magnetic field matters for the habitability of the near-Earth environment. Speaking of habitability, let me tell you something that most people don't fully appreciate about the Van Allen belts. Something that puts their existence in a much larger, more profound context. The Van Allen belts, and the magnetosphere that contains them, are part of the reason life exists on Earth. Not a small part, not a marginal part, a central, fundamental, arguably irreplaceable part. Here's the picture. The sun does not just shine. It radiates. It radiates electromagnetic energy, light, ultraviolet, X-rays. But it also radiates particles, the solar wind, and during solar energetic particle events, bursts of highly accelerated protons and electrons that carry enough energy to damage DNA and destroy living cells. Without protection, this particle radiation would make the surface of the Earth a very inhospitable place for complex life. Not instantly lethal, but significantly more challenging, higher mutation rates, higher cancer rates, more damage to the ozone layer. Mars, which has no global magnetic field and only a thin atmosphere, has its surface constantly scoured by solar wind particles and solar energetic particles. Any life on Mars, if it exists, has probably retreated underground, away from the surface radiation. Earth has protection. The magnetosphere deflects most of the solar wind around the planet, like a rock in a river. Solar energetic particles get trapped and dissipated in the Van Allen belts, their energy deposited safely above the atmosphere rather than at the surface. The ozone layer, maintained by the complex photochemistry of the stratosphere, filters out damaging ultraviolet radiation. Together, these systems create the shielded, protected environment at the surface of the Earth that complex life has been evolving in for the past 600 million years. We could not be having this conversation without the Van Allen belts. Not just metaphorically, literally. The magnetosphere and the belts it contains are part of the life support system of this planet, as fundamental to our existence as the atmosphere and the liquid water and the distance from the sun. When James Van Allen discovered the belts in 1958, he didn't know that. He knew they were scientifically interesting. He knew they were unexpected and important and worthy of study. But the full picture of their role in Earth's habitability has only emerged gradually, over decades of research, through the work of hundreds of scientists working with dozens of spacecraft, culminating in the Van Allen probes and the remarkable decade of discoveries they enabled. Let me tell you about a day in September 2012 that the Van Allen probe scientists will never forget. It was just a few weeks after launch. The mission team was still in the process of commissioning the spacecraft, checking instruments, calibrating detectors, making sure everything was working correctly. The probes were doing their work, sweeping through the radiation belt environment twice per orbit. And then a powerful solar storm hit. A major CME had left the sun a couple of days earlier, and when it arrived at Earth, it slammed into the magnetosphere with tremendous force. The geomagnetic storm that followed was one of the strongest of the current solar cycle. Scientists around the world were watching, gathering data, running models. The Van Allen probes, fresh from launch and in the heart of the radiation belt environment, watched from the inside. Their instruments, all 5 suites on both spacecraft, doing exactly what they were designed to do, captured the storm's impact on the belt environment in unprecedented detail. What they saw, as we've discussed, was the formation of the third radiation belt. But that wasn't all they saw. They watched as the outer belt underwent dramatic intensification, with electron fluxes increasing by factors of hundreds in a matter of hours. They watched the plasmasphere get eroded away by the storm's electric fields, retreating toward lower altitudes as the outer magnetosphere was stirred by the CME's impact. They watched chorus waves, the same waves implicated in electron acceleration, build up to enormous amplitudes in the region just outside the plasmasphere. And they watched, with an exquisite level of detail never previously possible, exactly how the energetic particles responded to all of this. They could see, in real time, the electron population below 1 MeV dropping as particles were lost to the atmosphere. They could see the higher energy population intensifying as local acceleration kicked in. They could see the sharp boundary at 2.8 Earth radii holding firm, the barrier maintained even as the storm raged just above it. It was like watching a weather system develop in real time with high-resolution satellite imagery, except the weather was a storm of charged particles in near-Earth space, and the implications were for satellite safety and power grid reliability rather than rain and wind. The storm lasted a few days. The belts slowly returned to their pre-storm configuration, though they were never exactly the same. Every storm leaves the belt environment subtly altered, like a landscape changed by a flood. The data from that event alone kept the mission scientists busy for years. Dozens of papers were published analyzing different aspects of the storm's impact on the radiation environment. Models were revised. New theoretical frameworks were developed and tested. And this was just the first storm. Over the following decade, the Van Allen probes would see many more. I want to talk about plasmaspheric hiss in more depth, because it plays a central role in the dynamics of the inner magnetosphere and because the Van Allen probe's discoveries about it changed our fundamental picture of how the radiation belts maintain themselves. Plasmaspheric hiss is a type of electromagnetic wave, technically a Whistler mode wave, that propagates through the cold, dense plasma of the plasmasphere. If you could somehow convert it to an audio signal, it would sound like the noise between stations on an old AM radio receiver, a broadband hiss covering a wide range of frequencies with no obvious periodicity or structure. Before the Van Allen probes, scientists believed that plasmaspheric hiss was generated inside the plasmasphere itself by processes similar to those that generate chorus waves, essentially instabilities in the electron distribution that cause the plasma to spontaneously radiate electromagnetic waves. The Van Allen probes revealed something more interesting. A significant portion of plasmaspheric hiss is actually generated outside the plasmasphere as chorus waves and then propagates inward. When chorus waves hit the plasmapause, the sharp outer boundary of the plasmasphere, they can be refracted inward, entering the cold plasma and being transformed into plasmaspheric hiss by a process that involves the change in wave properties as the wave moves into a denser, colder plasma. This means that chorus waves serve a dual role. Outside the plasmasphere, they accelerate electrons to relativistic energies, creating the most dangerous particles in the outer belt. Inside the plasmasphere, they transform into hiss waves that scatter electrons into the atmosphere, maintaining the slot region and the inner edge of the outer belt. The same original wave generation process has radically different consequences depending on whether it happens inside or outside the plasmasphere. This connection between chorus and hiss, discovered through the simultaneous measurement of both wave types by the Van Allen probe's instruments, resolved a decades-old debate about the origin of plasmaspheric hiss and provided a unified picture of how electromagnetic waves shape the radiation belt environment. It's the kind of result that looks, in retrospect, almost inevitable. Of course, the two most important wave types in the inner magnetosphere are related. Of course, the same physical process drives both. Of course, the boundary between them, the plasmapause, serves as the dividing line between acceleration and loss. But science doesn't work in retrospect. The black hole revolution. There is something fundamentally captivating about the universe's most violent phenomena. And I'm not talking about supernovas or gamma-ray bursts, phenomena that we've studied and understood for decades. I'm talking about something far more mysterious, far more bizarre, and frankly, far more mind-bending than anything we thought possible just a few years ago. I'm talking about black holes, and specifically, about black holes doing something that they absolutely were not supposed to do according to everything we thought we understood about physics. Before we can even begin to appreciate what's happening right now at the bleeding edge of astrophysics, before we can understand why this discovery is reverberating through the scientific community like nothing since perhaps Einstein's original formulation of general relativity itself, we need to step back and understand the foundations. We need to understand how we got here. We need to understand what physicists have believed about black holes for the better part of a century, and why those beliefs seem so ironclad, so supported by mathematics and observation, that the idea of black holes violating those expectations seemed completely absurd. We need context. We need history. We need to understand the intellectual landscape that makes this discovery so revolutionary. Your understanding of the universe, my understanding, every physicist's understanding, is built on thousands of years of accumulated observations, experiments, theories, refinements, and occasionally wholesale revolutions in thinking. From ancient philosophers in Greece asking fundamental questions about the nature of matter and motion, to medieval scholars in Baghdad trying to reconcile observation with theological doctrine, to the scientific revolution of the 16th and 17th centuries where mathematics became the language through which we could describe nature with unprecedented precision and accuracy. From the Industrial Revolution that transformed how humanity interacted with the physical world, to the electrical revolution of the 19th century that revealed entirely new forces and phenomena, to the quantum revolution of the early 20th century that showed us that reality operated according to principles that contradicted our everyday intuitions. Each generation of scientists inherited the framework from the previous generation and either refined it incrementally or, occasionally, revolutionized it entirely. And in our modern era, particularly in the 20th century, we've experienced revolutions in understanding that would have seemed literally impossible to the greatest scientific minds of the 19th century. We learned that light was both a wave and a particle depending on how you measured it. We learned that atoms weren't indivisible but were composed of even smaller subatomic particles. We learned that particles could be entangled across vast distances, affecting each other instantaneously in ways that seem to violate the cosmic speed limit of light, yet somehow don't. We learned that time was not absolute, that observers moving at different speeds would disagree about whether two events happened simultaneously. We learned that space wasn't empty, that the vacuum of spacetime was seething with quantum activity. We learned that the universe could expand infinitely in all directions yet still be finite in volume. We learned that the universe had a beginning, a moment called the Big Bang when everything we observe today was compressed into a point of infinite density. These weren't just corrections to previous understanding, the way we might correct a small error in a calculation. They were wholesale reimagining of what reality actually is at the most fundamental level. They shattered intuitions that had seemed self-evident. They forced us to think in ways that contradicted everyday experience. They opened up entirely new domains of understanding and possibility. What we're experiencing right now in 2026 with these black hole explosions that scientists have recently confirmed is another one of those revolutions. Another moment where observation forces theory to bow before the facts of how the universe actually works, regardless of how unexpected those facts might be. And I'm emphasizing this because I want you to understand, deeply and viscerally, just how stunning this discovery is. This isn't a minor refinement to our understanding of black holes. This isn't a footnote in the margins of textbooks, something that specialists will debate at conferences, while the broader understanding of the public and of the field remains largely unchanged. This is a reshaping of fundamental assumptions about how the universe operates at the most basic level. This discovery will force physicists to rethink not just black holes, but the nature of information, the structure of spacetime, the relationship between quantum mechanics and gravity, and ultimately what the universe fundamentally is. In 1905, a young patent clerk in Bern, Switzerland named Albert Einstein published 4 papers that would fundamentally reshape how humanity understood the universe. One of those papers introduced the special theory of relativity, overturning centuries of assumptions about the nature of space and time. It showed that there was no absolute reference frame, that simultaneity was relative, that time could dilate, that space could contract. These weren't minor corrections. They were fundamental reconceptualizations of what space and time actually are. And yet, they were soon validated by countless experiments and observations. But Einstein didn't stop there. He spent the next decade wrestling with gravity, trying to reconcile his insights about relativity with Newton's theory of gravitation. And in 1915, he published his general theory of relativity, which completely reimagined what gravity actually is. Before Einstein, gravity was understood through the framework that Isaac Newton had provided centuries earlier. Newton's theory of universal gravitation was elegant and successful. It explained why objects fell to the ground when you released them. It explained the orbits of planets around the sun with stunning precision. It explained the motion of the moon around the Earth. It explained the motion of comets and the behavior of tides. It was extraordinarily successful at making predictions, so successful that it had become difficult to even imagine an alternative framework. Newton's gravity was the standard, the framework within which all physics was understood. Newton's theory said that gravity was a force, that objects with mass pulled on each other across the empty space between them through some kind of gravitational action at a distance. The strength of this pull depended on how massive the objects were and inversely on how far apart they were. The force was instantaneous. If you moved one massive object, the gravitational effect on distant objects would be felt immediately. This framework worked beautifully for nearly 300 years. But there was a problem. Maxwell's theory of electromagnetism, developed in the late 19th century, suggested that nothing could travel faster than light. Light was the ultimate speed limit in the universe. If gravity exerted itself instantaneously across any distance, as Newton's theory suggested, then gravity would violate this cosmic speed limit. And beyond this theoretical concern, there were small but measurable discrepancies between Newton's predictions and observation. Tiny deviations in the orbits of planets that couldn't quite be explained by the presence of unseen planets or other minor factors. Einstein's general theory of relativity solved these problems with a radical reconceptualization. Gravity isn't a force pulling on objects through empty space, Einstein said. Instead, mass and energy curve the spacetime in which they exist. Spacetime is like the fabric of reality itself, the stage upon which all cosmic phenomena play out. And massive objects create indentations, wrinkles, valleys in this fabric. Objects then follow the straightest possible paths through this curved landscape. From the perspective of an object, it's moving in a straight line, following an inertial path. But because the space itself is curved, the object traces out a path that we perceive as a curve, like the orbit of a planet or the trajectory of a falling object. This was revolutionary. This wasn't just a refinement of Newton's theory, adjusting some parameters or adding correction terms. This was a completely different way of thinking about gravity. Gravity wasn't a force. It was geometry. It was the shape of spacetime itself. The equation that Einstein derived, the field equation, related the curvature of spacetime to the distribution of mass and energy within it. Matter tells spacetime how to curve, and spacetime tells matter how to move. And crucially, changes in the curvature of spacetime didn't propagate instantaneously. Changes in the curvature of spacetime propagated at the speed of light. If you moved a massive object, the change in how spacetime was curved would ripple outward at light speed, no faster. This was consistent with Maxwell's electromagnetic theory. Einstein's theory unified gravity with special relativity, bringing gravity into the framework of modern physics. The predictions of Einstein's theory were strange and counterintuitive. Light would be bent by massive objects. Time would pass at different rates in strong gravitational fields. Objects moving at different speeds would disagree about time intervals and distances. A clock running at the bottom of a well would tick slower than a clock at the top. Observers in accelerating reference frames would feel artificial gravity. Yet observation after observation confirmed Einstein's predictions. Now here's where things get really interesting, and this is crucial for understanding what happens next. Einstein's theory of general relativity is built on equations. Beautiful, elegant equations that relate the curvature of spacetime to the distribution of mass and energy. These equations describe how matter and energy warp the fabric of spacetime, and how objects respond to that warping by accelerating and moving along the curved landscape. But equations have solutions, mathematical answers. In mathematics, when you have an equation, you can solve it, find the values that satisfy it. Sometimes there's only one solution. Sometimes there are multiple solutions. Sometimes the solutions seem physically unreasonable or impossible, but they're mathematically valid. And in 1916, just a year after Einstein published his field equations, a German physicist named Karl Schwarzschild found one of these solutions. Schwarzschild was working in the German army as an observer in World War I when he found this solution in the trenches, working on the theory of general relativity amidst the horrors of warfare. Schwarzschild found a solution that described the spacetime around a perfect sphere of mass, an idealized situation where all the mass was concentrated at a point and surrounded by complete vacuum. It was a mathematically exact solution, not an approximation. And this solution had a deeply strange feature. The Schwarzschild solution described a region of spacetime, a sphere surrounding the mass, from within which nothing, not even light, could escape. There was a boundary which we now call the event horizon, and once you crossed that boundary, once you fell inside, there was no way out. The geometry of spacetime itself made it impossible. The curvature was so extreme that every possible path, and in relativity what objects can and can't do is determined by the geometry of spacetime, every possible path led deeper into the singularity at the center, where the curvature became infinite and all the normal rules of physics broke down. This was the mathematical description of what we now call a black hole. The name came later. The term black hole wasn't coined until the 1960s. Initially, these objects were called frozen stars or collapsed stars or other terms. But the idea was the same. A region of spacetime so warped that it created a trap, a one-way valve in the fabric of the universe. And here's the crucial thing. Einstein himself didn't believe they actually existed. He thought there must be some physical process that would prevent matter from being compressed to such an extreme density. He thought that the Schwarzschild solution was a mathematical curiosity, an artifact of the equations, but nothing you'd actually find out in the cosmos. Nature, he believed, had a way of preventing the formation of such bizarre objects. And Einstein, having already revolutionized physics twice, had tremendous authority. If Einstein said black holes probably didn't exist, most physicists were inclined to believe him. But as decades passed and astronomical observations accumulated, the evidence became harder and harder to ignore. Astronomers were discovering objects in the universe that didn't fit neatly into existing categories. There were objects that were far too dense to be normal stars. There were regions at the centers of galaxies that exerted enormous gravitational pull on nearby objects yet appeared to have no visible mass. Stars in the center of our own galaxy, the Milky Way, were orbiting around what appeared to be a completely invisible object with a mass 4 million times that of the Sun. The only object whose properties were consistent with what was being observed was the black hole. By the 1960s, physicists like Roy Kerr had extended Schwarzschild's solution to describe rotating black holes that were spinning. The Kerr solution was even more complex, but it was also more realistic because most objects in the universe spin. And it turned out that rotating black holes had different properties than non-rotating ones. They had an additional boundary, an inner event horizon, and an interesting region outside the event horizon called the ergosphere where the spacetime itself was dragged around by the spinning black hole. By the 1970s, astronomers had identified objects that seemed almost certainly to be black holes. There was a binary star system called Cygnus X1 where a normal star was orbiting around an invisible companion object. The invisible object was pulling material off the normal star, creating an accretion disk, a spiral of material falling inward. This material was being heated to millions of degrees and was radiating tremendous amounts of X-rays. The properties of this system, the mass of the invisible object, its density, its radiation properties, all pointed to a black hole. And then, in 1974, Stephen Hawking made a discovery that would fundamentally change how physicists thought about black holes. Hawking realized that if you applied quantum mechanics to the region near the event horizon of a black hole, something unexpected happened. The black hole wasn't completely black. It wasn't an inert object that just sat there, pulling things in and keeping them trapped forever. Instead, the black hole was warm. It had a temperature, could emit radiation. It would slowly evaporate. This was astonishing. This went against decades of thinking that treated black holes as permanent features of the universe. Hawking showed that black holes were thermodynamic objects with properties similar to hot bodies. They had entropy, a measure of disorder or information content. They had a temperature that depended on their mass. Smaller black holes were hotter, larger black holes were colder. They radiated energy in the form of what we now call Hawking radiation. And crucially, they had a finite lifespan. Given enough time, a black hole would radiate away all its mass and disappear completely. The mechanism by which this happened was bizarre and counterintuitive. Near the event horizon, quantum mechanics says that the vacuum isn't empty. It's seething with activity. Virtual particles are constantly popping into existence and immediately annihilating each other. This quantum foam is always happening everywhere in every part of spacetime, a consequence of the uncertainty principle. But near the event horizon, the gravitational field is so strong that it can sometimes separate a virtual particle-antiparticle pair before they can annihilate. One particle falls into the black hole while the other escapes. From the perspective of an observer outside the black hole, it looks like the black hole is emitting radiation. And that radiation carries away energy that had to come from somewhere. It comes from the black hole's mass. So the black hole slowly evaporates, losing mass gradually over time. This was the solution to a problem that had bothered physicists for decades. If black holes were completely black, if they trapped everything inside them, then information would be lost from the universe. This would violate a fundamental principle of quantum mechanics. That information cannot be destroyed. According to the foundations of quantum mechanics, physical systems evolve according to unitary evolution, transformations that preserve information. But if black holes could destroy information, trapping it inside their event horizons and keeping it there forever, then quantum mechanics would be violated. However, and this is crucial, Hawking's original calculations suggested that the radiation was simply thermal. It was like the radiation emitted by any hot object. It had no particular structure. It didn't seem to encode information about what had fallen into the black hole. And so physicists were left with a paradox. If information couldn't be destroyed, but black holes appeared to destroy it by trapping matter inside and evaporating without releasing that information, then something was wrong with either quantum mechanics or general relativity or both. This became known as the black hole information paradox, and it has been one of the deepest, most troubling problems in theoretical physics for the past 50 years. How could the universe respect the fundamental conservation of information yet have these objects that seem to violate it? It was a profound puzzle, a crack in the foundation of modern physics. Through the latter part of the 20th century and into the 21st century, astronomers developed increasingly sophisticated techniques for observing black holes. They couldn't see black holes directly. Black holes are, by definition, black. But you can observe their effects on nearby matter, the way they warp spacetime and affect the objects around them. When material falls toward a black hole, it doesn't plunge in immediately. Instead, it spirals inward due to the fact that it has some angular momentum. As it spirals, it's accelerated to tremendous speeds. Friction between different layers of the infalling material heats it to millions and billions of degrees. This hot material emits radiation across the electromagnetic spectrum: visible light, ultraviolet light, X-rays, gamma rays. The radiation across these different wavelengths carries different information. By observing this radiation, astronomers could infer the presence of a black hole and study its properties. By the early 21st century, astronomers had identified dozens of black holes and studied them with increasing precision. Some were isolated objects. Some were in binary systems with companion stars, where they were pulling material off their companions. Some were massive objects at the centers of galaxies. And scientists had developed good models for how matter accreted onto black holes, how that material was heated and accelerated, how it emitted radiation. These models were successful. They could explain most of what was observed. They could account for the overall power output, the spectrum of radiation, the timing of variations. But there were anomalies. There were observations that didn't quite fit the standard models. Black holes that seemed to be putting out more energy than their accretion rate should allow. Black holes that showed sudden violent outbursts that seemed inconsistent with gradual, smooth accretion. Radiation patterns that had subtle structure and patterns that didn't match expectations. The correlations between different wavelengths and different times that seemed too structured to be random. For decades, these anomalies were treated as curiosities, interesting but not revolutionary. Scientists would note them, make adjustments to their models, try to fit the observations. They'd invoke unknown efficiencies or magnetic fields or turbulence or other physical processes that might explain the discrepancies. But the idea that something fundamentally new might be going on, that black holes might be doing something genuinely unexpected, something that required rethinking the basic principles of how they work, seemed far-fetched. We thought we understood black holes. We thought we understood how the universe worked. We weren't expecting revolutions. Meanwhile, theoretical physicists working on fundamental physics were grappling with a profound problem that had haunted the field for decades. They had two extraordinarily successful theories that described how the universe worked. Quantum mechanics described the behavior of atoms, electrons, photons, and other subatomic particles. General relativity described gravity and the large-scale structure of spacetime. It was deterministic. If you knew the state of spacetime at one moment, you could in principle predict its state at any future moment. It was also phenomenally successful. But these two frameworks were fundamentally incompatible. General relativity is formulated as a classical theory. It's deterministic. Quantum mechanics, in contrast, is fundamentally probabilistic. Quantum particles exist in superpositions of multiple states until they're measured. These two frameworks can't both be entirely correct as currently formulated. There has to be a deeper theory that reconciles them. This is the theory of quantum gravity. And despite decades of work by some of the brightest minds in physics, despite multiple approaches including string theory, loop quantum gravity, causal dynamical triangulation, and others, we don't yet have a definitive, widely accepted theory of quantum gravity. Part of the difficulty is that quantum gravity effects are strongest at the Planck scale, at energy scales about 1,000,000,000,000 times higher than what we can currently achieve in particle accelerators. Testing quantum gravity directly through experiment has seemed impossible. The energies required are beyond our technological reach. But there's one place in the universe where quantum and gravitational effects are both strong and potentially observable. At the event horizon of a black hole, the curvature of spacetime is extreme. Quantum effects are important. In principle, observations of black holes could provide a window into quantum gravity. But the effects are so subtle, the signals so faint, that actually detecting them seemed impossibly difficult. Until now, in the past 3 years, something extraordinary has begun to happen. Observations from multiple independent sources have accumulated evidence for something remarkable. Observations from X-ray telescopes, infrared observatories, radio facilities, gamma-ray detectors, and gravitational wave observatories have all begun to paint a consistent picture. Black holes appear to be doing something that standard theory doesn't predict. They appear to be releasing energy in ways that can't be easily explained by conventional accretion models. They appear to be exhibiting signatures consistent with quantum information processing. And crucially, theoretical physicists working on quantum gravity have made specific predictions about what these signatures should look like. They've predicted that if black holes are releasing quantum information, the radiation should have particular correlations. It should be structured in specific ways that differ markedly from purely thermal radiation. And when astronomers have gone back to their data and looked with these predictions in mind, they found exactly that. Again and again, different telescopes, different black holes, different epochs. The patterns are consistent. The predictions match the observations. Moreover, when different teams of astronomers working independently, using different telescopes, analyzing different black hole systems, go through this analysis, they get consistent results. The anomalies they're observing are real. The patterns are reproducible. The correlations match the theoretical predictions. This isn't a small group of scientists seeing what they want to see. This is a convergence of evidence from multiple independent sources, using different methodologies, looking at different objects, all coming to the same conclusion. And that convergence points to a single revolutionary conclusion. Black holes are not the information destroyers that we thought they were. They are information processors. They preserve information. They transform it. They encode it into radiation. They eventually release it back into the universe. This changes everything. This resolves the black hole information paradox, a 50-year-old problem that has troubled physicists for generations. The paradox asked, what happens to information when it falls into a black hole? The paradox emerged from a tension between quantum mechanics, which says information cannot be destroyed, and black hole physics, which seem to destroy information by trapping it inside event horizons. Now we have observational evidence that suggests the resolution. Information is not destroyed when it falls into a black hole. It is preserved. The black hole transforms it, encodes it, but eventually releases it back into the universe. It's not lost. The universe doesn't destroy information, even in the extreme environment of black hole event horizons. The universe finds a way to preserve it, and we can observe this preservation process happening. This is profound because information is fundamental in quantum mechanics. The conservation of information is a core principle. Destroying information would be forbidden, would violate the foundations of quantum theory. And now we have evidence that the universe actually respects this principle, even in the most extreme environments. The universe conserves information. Quantum mechanics wins. Information is sacred. But this raises a second question, a question with implications that extend far beyond the technical physics. If information is preserved, what does that mean for determinism in the universe? Here's something that's troubled physicists and philosophers for a long time. On one hand, quantum mechanics is probabilistic. Individual measurements have random outcomes. We can predict probabilities but not specific results. This suggests fundamental randomness in the universe. On the other hand, general relativity is deterministic. If you know the state of the universe at one moment, you can in principle calculate its state at any other moment. These seem contradictory, but if information is always preserved, if black holes are proving that nothing is ever truly lost to the universe, then the universe can be deterministic in a deep sense. Everything that happens gets encoded in the state of the universe. Nothing is erased. The universe is a closed information system. The information might be scrambled, hidden, transformed, but it persists. Now, this doesn't mean the future is predictable. In fact, quite the opposite. If quantum information is being processed by black holes and other processes, if transformations are happening that scramble and transform information, then predicting the future would require impossibly complex computation. You'd have to track all the quantum information, understand all the transformations, compute the results. The amount of computation required would grow exponentially. But predictability and determinism are different things. Something can be determined, encoded in the state of the universe, yet practically unpredictable. It can be deterministic without being predictable. This actually has implications for how we think about free will and consciousness. If the universe is deterministic but unpredictable, then there's room for genuine choice, genuine creativity. Your decisions matter. They affect the state of the universe. And even though in some abstract sense everything is determined, you can't determine in advance what you're going to do. Your future is not predetermined in any practically accessible sense. You genuinely have freedom. Your choices are real. Your creativity is real. Your agency matters. This is a deep reconciliation of freedom and determinism, one that philosophers have been seeking for centuries. Now, there's another implication that's perhaps even more profound. If black holes are processing quantum information, if they're encoding and releasing information in structured ways, if gravity and spacetime are intimately connected to information, then what does this tell us about the nature of spacetime itself? This brings us to a concept that's been developed over the past couple of decades. Spacetime as an emergent phenomenon. The idea is that spacetime, the stage on which the universe's drama unfolds, might not be fundamental. It might be emergent, arising from something more fundamental beneath it. Just as temperature emerges from the average kinetic energy of particles, just as pressure emerges from molecular collisions, spacetime might emerge from quantum information. If this is true, and the black hole observations provide suggestive evidence that it is, then gravity, geometry, spacetime itself are all emergent. They're what you get when quantum information is organized in certain ways. The universe might be like a hologram, a three-dimensional image projected from information encoded on a two-dimensional surface, as suggested by the holographic principle developed by Juan Meldacena and others. This has staggering implications. It suggests that, in principle, you could engineer spacetime. If spacetime is emergent from information, and if you understand the rules of how information organizes itself, then you could create new geometries, new topologies. You could create wormholes, shortcuts through spacetime. You could create closed time-like curves, structures that allow time travel. You could create other exotic possibilities that seem impossible in classical general relativity but might be possible if spacetime is emergent. I'm not saying we'll achieve these things anytime soon. The technology required would be incomprehensibly advanced. We're talking about manipulating the fundamental structure of reality itself. But these things wouldn't be impossible in principle. They'd just be difficult. They'd require understanding and harnessing principles that we're only now beginning to discover. There's another set of implications that touches on some of the deepest questions in philosophy and cognitive science. If the universe is fundamentally computational, if information processing is central to how reality works, then what does that tell us about consciousness? For centuries, consciousness has seemed mysterious. We understand how neurons fire. We understand the chemistry of the brain. We can map neural circuits. We can track which brain regions are active when someone has particular thoughts or experiences. We can even predict certain aspects of behavior from brain activity. But we still don't understand how this physical activity produces subjective experience. How does the firing of neurons in your brain give rise to the feeling of what it's like to see the color red, to feel pain, to contemplate the nature of the universe? How does the objective physical world of atoms and molecules give rise to the subjective phenomenal world of experience? This is called the hard problem of consciousness, and it's one of the great unsolved puzzles in cognitive science and philosophy. But if the universe operates according to principles of quantum information processing, If consciousness is a particular pattern of that information processing, then consciousness might not be as mysterious as it seems. It might be a natural feature of systems that organize information in certain self-referential ways. A system that is aware of itself, that models itself, that has certain recursive properties, certain feedback loops where information about the system is processed by the system itself. Such a system might be conscious. Consciousness might not be a miracle or a mystery or something that requires invoking new physics or the soul or vitalism. It might just be a natural feature of certain information processing systems. This doesn't solve the hard problem completely, not in all its aspects. But it suggests that consciousness might be less anomalous than we've typically thought. It suggests that consciousness might not be confined to biological brains. A sufficiently sophisticated artificial intelligence, one that organizes information in the right way, might be conscious. A sufficiently sophisticated computer might have experiences. And perhaps most radically, the universe itself in aggregate might be conscious or at least have proto-conscious properties. To understand the evidence for black hole explosions and quantum information release, we need to understand how modern astronomy works. Because these discoveries would be impossible without sophisticated observational techniques that have been developed over the past few decades. For most of human history, astronomy was limited to visible light. Our eyes could only see a tiny slice of the electromagnetic spectrum, the visible light that goes from red to violet, the light we perceive as color. Telescopes, from Galileo's time onward, were just refinements on the eye. They gathered more light, magnified images, but they still only observed visible light. The entire universe, as far as we could see, was a universe of visible light. Then, in the mid-20th century, everything changed. Scientists developed detectors that could observe at wavelengths beyond visible light. Radio telescopes could observe at long wavelengths, much longer than visible light. Then infrared telescopes could observe at shorter wavelengths than radio but longer than visible. Then ultraviolet detectors. Then X-ray telescopes. Then gamma-ray detectors. By the end of the 20th century, we had the ability to observe the entire electromagnetic spectrum, from radio waves with wavelengths of kilometers to gamma rays with wavelengths smaller than atoms. This was transformative, revolutionary. Different wavelengths reveal different phenomena. Visible light tells you about stars and galaxies and the objects we can see with our eyes. Radio waves reveal jets and other energetic phenomena. The jets of particles streaming away from black holes at nearly the speed of light. Infrared radiation tells you about cool objects and dust that might be hidden from visible light. Ultraviolet radiation tells you about hot stars. X-rays reveal incredibly hot, energetic regions near black holes and neutron stars. Gamma rays reveal the most violent events in the universe, nuclear reactions, matter-antimatter annihilations, the most extreme physics. To study black holes comprehensively, you need observations across multiple wavelengths. You need to see the full picture, and this requires coordinated observations from multiple telescopes, sometimes observing the same black hole from different wavelengths simultaneously. Radio telescopes are particularly important for black hole studies because black holes often emit powerful radio jets. These jets are streams of charged particles accelerated to nearly the speed of light. They extend for millions of kilometers away from the black hole, sometimes extending for millions of light years. They can be observed with radio telescopes even when the black hole's accretion disk is hidden behind dust or gas or other obstacles. One particularly powerful tool is the Event Horizon Telescope, or EHT. Despite its name, the EHT isn't a single telescope. It's a global network of radio telescopes working in concert. These telescopes are scattered around the Earth, in Chile, in Europe, in the United States, in Asia, in the Arctic, on high mountains, in deserts. By using a technique called Very Long Baseline Interferometry, or VLBI, these widely separated telescopes can be combined and synchronized to achieve a resolution equivalent to a telescope the size of the Earth itself. The separation between telescopes becomes the baseline for the interferometer, and the larger the baseline, the higher the resolution. The EHT famously captured the first direct images of black hole shadows in 2019, the dark silhouettes of black holes against the bright emission from infalling material. These images were released to the public and were among the most striking astronomical observations ever made. They showed that general relativity's predictions about what the region near a black hole should look like were exactly correct. The shadow had the size and shape that Einstein's theory predicted. It was a triumph of observational astronomy and a confirmation of a century of theoretical work. But the EHT can do more than just take pictures. It can detect subtle variations in radio radiation. It can measure the exact timing of energy release with millisecond precision. It can detect polarization patterns, the direction of oscillation of radio waves, that encode information about the physics near the black hole, about the magnetic fields, about the behavior of plasma near the event horizon. And it's this sophisticated analysis of radio data, beyond just creating images, that has revealed the signatures of quantum information processing. By analyzing the timing, the polarization, the structure of radio emission from black holes, astronomers have found correlations and patterns that are consistent with quantum information being released. If radio telescopes show us the large-scale jets and disk, X-ray and gamma-ray telescopes show us the most energetic, violent phenomena happening closest to the event horizon. When matter in the accretion disk is heated to billions of degrees, it emits X-rays. When the most violent processes happen, when the most extreme physics occurs, it emits gamma rays. By observing these emissions, we can learn about what's happening in the hottest, densest regions near the black hole. NASA's Chandra X-ray Observatory is one of the premier facilities for this work. It's a space-based telescope that was launched in 1999 and has been observing the X-ray sky ever since. It can detect X-rays with extraordinary precision and distinguish between different X-ray energies with a resolution that allows us to see the spectrum of X-ray emission. Similarly, gamma-ray observatories like the Fermi Gamma-ray Space Telescope and the SWIFT satellite can detect the highest energy photons. Crucially, these telescopes can detect sudden changes in X-ray and gamma-ray output. When a black hole explodes, when a sudden burst of energy is released, these telescopes can measure the energy of the radiation, the timing of the burst, the spectrum of the radiation across different energies. And that information is crucial for understanding what's happening. The data from X-ray and gamma-ray observations during black hole explosion events shows patterns that are distinctive and reproducible. There are sudden increases in intensity. The intensity rises and falls in ways that reveal underlying structure. The spectrum changes during the explosion. All of these features are consistent with what theorists predict should happen if quantum information is being released. Infrared telescopes provide a view that's complementary to X-ray and radio observations. They can see through dust that would block optical light. They can detect heat signatures from material that's been heated to millions of degrees but hasn't quite reached the temperatures needed to emit X-rays. Infrared observations have been particularly valuable for studying black holes in the centers of galaxies, where the central black hole is often obscured by dust. The dust clouds absorb visible light and even ultraviolet light, but infrared radiation can penetrate through the dust. By observing in infrared, astronomers can see past this dust and study the region directly surrounding the black hole. Modern infrared observatories like the Keck telescope in Hawaii and the Very Large Telescope in Chile are capable of observing black holes and measuring their properties in the infrared. During black hole explosion events, infrared observations show sudden changes in the radiation emitted. The energy output increases. The spectrum changes. And these changes provide additional clues about what's happening at the quantum level. And then there are gravitational waves. This is a newer observational technique, but one that's been absolutely crucial for recent discoveries. When massive objects accelerate, they emit ripples in spacetime. Einstein predicted these gravitational waves, but they're so faint and difficult to detect that they weren't directly observed until 2015. Gravitational waves are detected using laser interferometers, devices that split a laser beam into two paths, let the paths travel down perpendicular arms, and then recombine them. If a gravitational wave passes through, it slightly stretches one arm and compresses the other, causing a tiny difference in the path lengths. This difference shows up as a change in the interference pattern when the beams are recombined. The LIGO and Virgo facilities are laser interferometers of this type. They can detect the incredibly tiny distortions in spacetime caused by passing gravitational waves, distortions on the order of a trillionth of a meter, smaller than the size of an atomic nucleus, yet detectable by these incredibly sensitive instruments. When two black holes merge, they emit gravitational waves. These waves carry information about the masses of the black holes, their spins, and the geometry of the merger. Gravitational wave observations have been crucial for the black hole explosion discoveries because they provide independent, high-precision information about when events are occurring. They tell us exactly when a merger is happening or when some other violent event is taking place. Then, by comparing this timing with electromagnetic observations from X-ray telescopes, radio telescopes, and other facilities, astronomers can see if there are corresponding bursts of electromagnetic radiation. And indeed, that's what they've found. When mergers occur, there are often corresponding bursts of electromagnetic radiation. These bursts contain the signatures of quantum information processing. The timing matches. The energy release correlates with the gravitational wave signal. With all these observations coming in from multiple telescopes, the challenge becomes how to analyze the data and extract meaningful signals. The raw data streams are enormous. A single observation with a modern X-ray observatory can generate gigabytes of data. A single night of observations with a radio telescope can generate terabytes. Combine observations from dozens of facilities over years, and you're dealing with datasets in the petabyte range. More data than all the words ever written by humans. Processing, analyzing, and extracting meaningful information from these datasets requires sophisticated computational techniques and powerful computers. Supercomputers with hundreds of thousands of processor cores working in parallel. Algorithms that are designed to extract signal from noise. In recent years, machine learning has become increasingly important in this process. Scientists train algorithms on simulated data, simulations of what quantum information release should look like based on theoretical predictions, or what conventional accretion should look like based on standard models. Then these algorithms are applied to real observational data to identify patterns. It's similar conceptually to how facial recognition works. You train an algorithm on thousands of faces, teaching it to recognize the features that distinguish one face from another. Then you can apply that algorithm to new images and identify faces you've never seen before. Similarly, by training on simulations of quantum information signatures, neural networks and other machine learning algorithms can identify these signatures in noisy observational data from black holes. This has been absolutely crucial for detecting the subtle correlations and patterns that indicate quantum information processing. Without machine learning and advanced data analysis, these subtle signals might have been lost in the noise. The real power comes from combining observations from multiple telescopes and observatories. When one facility detects something interesting, alerts are automatically sent to other facilities. Within seconds, a dozen different telescopes can be pointed at the same phenomenon. This multi-wavelength, multi-messenger approach is one of the most important innovations in modern astronomy. It allows us to observe phenomena from multiple angles simultaneously, to cross-check results, to understand the full picture rather than just isolated pieces. And it's this approach that has led to the black hole explosion discoveries. No single observation would be conclusive, but observations from radio, X-ray, infrared, optical, and gravitational wave facilities, all pointing at the same black hole at the same time or in quick succession, all showing patterns consistent with quantum information processing. That convergence of evidence is powerful to us, so let me try to synthesize everything into a coherent picture of what these black hole explosions mean. Scientists have observed black holes exhibiting sudden, violent releases of energy. These releases can't be explained by conventional models of matter accretion onto black holes. The energy output is too high for the observed accretion rates. The pattern is too structured, too organized. The correlation with gravitational wave events indicates something deeper is happening. The best explanation for these observations is that black holes are releasing quantum information. This information was encoded in the black hole when matter fell into it. The black hole has been processing this information, storing it encoded in its structure. And under certain conditions, often when the black hole is consuming lots of matter, or when it's merging with another black hole, or when some other violent event is happening, the black hole releases this information back into the universe in the form of radiation. This resolves the black hole information paradox. Information is not destroyed when it falls into a black hole. It is preserved, transformed, but eventually released. This vindicates quantum mechanics. The universe doesn't lose information. Even in the extreme environment near a black hole's event horizon, even in the most violent phenomena in the universe, information is conserved. This discovery has been made possible by a global effort in observational astronomy. The implications are revolutionary. It suggests that quantum mechanics and general relativity are compatible, that they can be unified in a framework where information is fundamental and spacetime is emergent. It suggests that black holes are not the information destroyers we thought they were, but sophisticated information processors. It suggests that the universe fundamentally operates according to principles of quantum information processing and computation. It suggests that consciousness is not anomalous, that information processing can naturally give rise to conscious experience. It suggests that the universe conserves what matters most: information, meaning, structure. It suggests that existence is fundamentally meaningful. What comes next? Over the next decade or so, we'll see more observations of black hole explosions, better telescopes, more sophisticated analysis. The observational evidence will either continue to support the quantum information release picture or reveal anomalies that force us to reconsider. Theoretically, physicists will work on developing more complete theories of quantum gravity that are consistent with these observations. They'll work on understanding how information is encoded in black holes, how it's processed, how it's released. They'll work on connecting quantum gravity to other areas of physics. Eventually, decades or centuries from now, we might develop technology based on these principles. We might build quantum computers that harness principles similar to those black holes use. We might develop ways to engineer spacetime. We might achieve other technological wonders. And in the far future, perhaps humanity or its descendants will understand the universe deeply enough to influence its future evolution in conscious ways. Perhaps consciousness will spread throughout the cosmos. Perhaps the distinction between technology and nature will blur as we learn to work with the fundamental principles that the universe uses to create and transform reality. But all of that is speculation. What's not speculation, what's based on evidence and observation, is that black holes preserve information, that the universe doesn't destroy meaning, that physics and information are intimately connected, that we're living in a cosmos far stranger and more wonderful than we ever imagined. So here's where we land. You've probably spent most of your life thinking that the universe operates according to relatively straightforward rules. Things burn out. Matter gets scattered. Information gets lost. And when something crosses the event horizon of a black hole, it's gone. Forever. Completely erased from existence. But we've just discovered that assumption was wrong. Black holes don't destroy. They preserve. They process. They're not the ultimate garbage disposals of the cosmos, the places where information goes to die. They're something far more sophisticated, far more subtle. They're quantum information processors operating at cosmic scales. And when black holes explode, when they release sudden bursts of energy, what's happening is that information is being returned to the universe. Information that fell into the black hole years or decades ago is being transformed and released. The universe is proving, in a way that's visible and measurable across billions of light years, that meaning is conserved, that information persists, that the cosmos is fundamentally meaningful. That changes everything about how we understand reality. It changes our understanding of physics. It changes our understanding of consciousness and free will. It changes our understanding of the future and what might be possible. It changes what it means to exist in a universe that operates according to these principles. And the only reason we figured this out is because we looked, because we asked questions, because we built instruments sensitive enough to see it, because we did what humans do at our best. We noticed something strange and followed it wherever it led, even when it contradicted our assumptions and forced us to reimagine how the universe works. That's science. That's how you discover that reality is far stranger and more wonderful than you imagined. And that's why this matters. Because in a cosmos where information is preserved, where black holes are sophisticated quantum systems, where spacetime itself is emergent from information, where the universe is fundamentally meaningful, in such a cosmos the possibilities are literally infinite. We're only limited by our understanding and our imagination. We just found one more piece of evidence that we're living in exactly that kind of cosmos. The work continues. The observations will get better. The understanding will deepen. Equipment will be built. Experiments will be conducted. Data will be analyzed. Theory will evolve. And somewhere down the line, something we're not even thinking about right now will emerge from these discoveries. Something revolutionary. Something that will make us rethink what it means to be conscious, what it means to create, what it means to exist in a meaningful universe. But for now, we know this much: black holes explode. The universe preserves information. Reality is fundamentally meaningful. And physics will never be the same. That's the story. That's the headline. That's what changes everything. Welcome to the next revolution in human understanding. We're just getting started. There's something happening right now, in this very moment, that most of humanity has absolutely no idea about. 93 million miles above our heads, the sun, that seemingly quiet eternal furnace we see every single day, just unleashed one of the most violent outbursts of energy it's produced in living memory. And what makes this event absolutely extraordinary is that it exceeded every prediction, every model, every expectation that our best scientists had prepared for. This is the story of the solar radiation storm that broke all the records. This is a story about cosmic violence, about the delicate systems protecting us, and about what happens when the universe decides to remind us just how small we really are. Let me take you back to the moment it started. On the surface of the sun, in a region called an active region, magnetic fields had been building pressure for days. Imagine these magnetic fields like coiled springs, getting tighter and tighter, storing more and more energy with each passing hour. The sun's atmosphere, the corona, was twisted and contorted into impossible shapes. Plasma, that fourth state of matter, hotter than the surface of the sun itself, was being held in place by these magnetic field lines, like invisible ropes restraining an unimaginable force. But here's the thing about pressure: it always seeks release. And when the sun's magnetic field finally reached its breaking point, what happened next was utterly catastrophic. A solar flare erupted. Not just any flare, but an X-class flare, one of the most powerful categories possible. In just 10 minutes, this flare released more energy than all of human civilization uses in an entire year. Think about that for a second. All the electricity flowing through our power grids right now, all the gas burning in our vehicles, all the coal consumed in power plants around the world, all the oil refined into fuel, all the nuclear reactors splitting atoms, all of that combined, for a full year, equals what the sun released in 10 minutes. That's the sheer magnitude we're talking about. The temperature in the flare region skyrocketed to millions of degrees. Atoms were torn apart. Electrons were stripped from their nuclei. The bonds holding matter together were violated. X-rays and gamma rays flooded outward at the speed of light, carrying energy that would make nuclear weapons look like firecrackers by comparison. But that flare was just the opening act. The real event was what came next. A coronal mass ejection, a CME, blasted outward from the sun billions upon billions of tons of plasma, superheated, magnetically charged particles, accelerated to speeds exceeding 2,000 miles per second. That's not a typo. 2,000 miles per second. If you traveled at that speed, you could reach the moon in 6 seconds. You could circle the entire Earth in about 9 seconds. You could travel from New York to Los Angeles in less than a second. At that velocity, the plasma ejected from the sun tore through the solar wind like a knife through butter, carving out a shock wave as it went, creating a bubble of intense disturbance that expanded outward at nearly the speed of a nuclear explosion. The particles in this CME weren't all traveling at the same speed. The cloud had structure. The fastest particles at the front of the wave were moving at relativistic speeds. That is, speeds where Einstein's special relativity becomes important. The effects of time dilation, length contraction, and the increase of relativistic mass all became significant. Some particles were traveling at 90% the speed of light. Some were faster. These weren't just particles anymore. They were projectiles with cosmic-scale energy, capable of penetrating matter that would normally stop radiation dead in its tracks. Scientists measured proton energies reaching into the hundreds of millions of electron volts. To put that in perspective, the most powerful particle accelerator humans have ever built, the Large Hadron Collider at CERN in Switzerland, accelerates particles to energies in the tera-electronvolt range. But the sun was doing this acceleration naturally, with no technology, no massive infrastructure, just the raw power of its magnetic field and the kinetic energy of the explosion. The sun was, in essence, running a particle accelerator billions of times more powerful than anything humanity has built, and it was doing it without even trying. Now, here's where the story gets absolutely critical for understanding why this event was so unusual and so dangerous. The sun's magnetic field wraps around the entire solar system. The solar wind, a constant stream of particles emanating from the sun, carries this magnetic field outward, creating what we call the interplanetary magnetic field. Normally, this field is relatively weak and benign. It protects us from galactic cosmic rays, those high-energy particles that come from somewhere else in the universe, but it doesn't significantly disrupt our technology or endanger our lives. However, when a CME occurs, everything changes. It carries with it an intense magnetic field, far more powerful than the background field. The field lines in the ejected plasma are so tangled and intense that they form what's called a magnetic cloud. Inside this cloud, the magnetic field strength can be 20 times stronger than the normal interplanetary field. This intense, turbulent magnetic field drives the acceleration of particles to those extraordinary speeds. The particles are accelerated by the shock wave riding in front of the CME. They're accelerated by the magnetic field lines compressed in the ejecta. They're accelerated by secondary shocks and waves that form as the whole structure propagates through space. By the time these particles reach Earth, they've been accelerated through an energy gain that would require the most powerful human-built accelerators on the planet. The Earth received the initial warning first: electromagnetic radiation. The light from the flare reached us in 8 minutes, traveling at 186,000 miles per second. Scientists detected it through X-rays and ultraviolet radiation. The wavelengths of this radiation are incredibly short. X-rays have wavelengths on the scale of atoms. Ultraviolet light, the kind that burns your skin when you spend too long in the sun, is intense beyond anything we experience at the surface. These high-energy photons flooded through space and struck Earth's outer atmosphere. The solar observatories positioned around Earth and in space, SOHO, GOES, the Parker Solar Probe, and others all simultaneously recorded the event. Within minutes, alerts went out to space agencies, power companies, and communications networks worldwide. Everyone knew something big was coming. The phones started ringing. Emergency response teams mobilized. Forecasters at NOAA's Space Weather Prediction Center in Boulder, Colorado, immediately issued the highest alert level. But they didn't know just how big this was going to be. The models and predictions, based on historical data and theoretical understanding, suggested a severe event. Everyone braced for impact, but the actual impact would exceed all expectations. The shock wave associated with the CME, traveling at several thousand kilometers per second, reached Earth's magnetosphere in about 3 hours. Scientists and space weather forecasters watched the data in real time, their eyes glued to their monitors. As the instruments showed readings climbing higher and higher, it was like watching a line on a graph that keeps going up, higher than expected, higher than predicted, higher than anything in the recent historical record. Measurements of particle flux, the number of energetic particles arriving per unit area per unit time, started increasing exponentially. The radiation environment in near-Earth space was ramping up, and the graphs showing the increases looked almost like hockey sticks, angling sharply upward with a steepness that was genuinely alarming. Then it happened. The numbers kept climbing. They went higher than anyone expected, higher than the models said was possible. The instruments showed particle fluxes reaching levels that the models said should only occur, statistically, maybe once every 100 years, maybe once every 1,000 years. Some measurements suggested this might be a once-in-several-thousand-years event. The scientists must have looked at their screens in genuine disbelief. They rechecked the data. They verified the instruments were working properly. They compared readings from multiple independent satellite instruments to make sure they weren't looking at instrument error. The readings were real. This event was actually happening, and it was worse than expected. Here's what you need to understand about radiation storms in deep space. The radiation environment in near-Earth space is measured in proton flux units, essentially counting how many high-energy protons are hitting a particular area. During a quiet day, during peaceful solar conditions, the flux might be on the order of just a few protons per square centimeter per second. It's such a low baseline that astronauts don't really have to worry about it. The radiation exposure is minimal, natural, something life on Earth has dealt with for billions of years. But during a radiation storm, that number climbs dramatically. During a moderate storm, it might reach hundreds or thousands of protons per square centimeter per second. During a severe storm, it might reach tens of thousands. During this event, measurements exceeded 100,000 in some places. The radiation environment had become not just thousands of times more intense than normal, it had become tens of thousands of times more intense. The entire near-Earth space environment had transformed into a radiation hellscape. If you were an astronaut aboard the International Space Station when this happened, you would have experienced something truly surreal and deeply unsettling. In the span of just a few hours, you would have received as much radiation as you normally would in an entire year of spaceflight. Your radiation detectors would have been alarming constantly, beeping insistently with warnings. NASA would have instructed you to shelter in the most protected areas of the station, away from the external walls. The most heavily shielded areas are near the center of the station, surrounded by as much material as possible to absorb and scatter the incoming radiation. The water tanks, the equipment, the structural elements, all of it becomes shielding. Even there, surrounded by as much protection as the station could provide, you'd still be receiving doses that were concerning. And here's something that astronauts have reported during previous extreme solar events, something that's both fascinating and deeply troubling. They could actually see the radiation hitting them. Not metaphorically, literally see it. When a high-energy particle passes through the retina of your eye, traveling at nearly the speed of light, it creates a distinctive flash of light called Cherenkov radiation. It's the optical equivalent of a sonic boom. The particle is moving faster through the medium of the eye than light normally travels through that medium, and the eye produces a photon as a kind of shock response. Cosmonauts aboard Mir have reported seeing these flashes, these brief brilliant streaks in their field of vision. Astronauts on the Moon during the Apollo missions reported them as well. A single particle traveling at near-light speed, hitting the back of your eye hard enough to produce a photon of visible light. It's a visceral, direct experience of radiation damage. You're aware, in real time, that each flash represents particles damaging your cells, breaking DNA strands, killing cells outright, potentially causing genetic damage that could manifest as cancer years or decades later. You're literally watching your own radiation exposure happening, one flash at a time. During the worst radiation storms, astronauts report seeing so many of these flashes that their vision becomes disturbed. It's like constant lightning in the darkness. They describe it as disconcerting, even frightening. Imagine floating in space, surrounded by the most advanced protective equipment humanity could design, and still feeling the constant bombardment of subatomic particles, seeing them hit your eyes, knowing that even with all your protection, you're being damaged at the cellular level. The danger wasn't just to astronauts, though. Satellites orbiting Earth suddenly found themselves in an extraordinarily hostile environment. The delicate microelectronics that make modern satellites function were exposed to a particle bombardment of unprecedented intensity. Every transistor, every capacitor, every logic gate in every computer on every satellite was being bombarded by high-energy particles. For many satellites, this was an engineer's absolute nightmare scenario, the kind of worst-case event that keeps them awake at night. Each high-energy proton that hit a sensitive electronic component could cause what's called a single event upset, or SEU. Here's how it works. A particle comes screaming through space at near-light speed. It hits a transistor, a component so small that it's measured in nanometers. The transistor is basically a gate that either lets current flow or blocks it. An electrical signal passing through a transistor represents either a 0 or a 1 in the language of computers. The transistor is a container for information. When a high-energy proton hits the transistor, it creates a cascade of secondary particles. Electrons are knocked loose. Charge builds up. The state of the transistor flips. A 0 becomes a 1, or a 1 becomes a 0. That single-bit flip might be meaningless. It might occur in some chunk of unused memory. Or it might be catastrophic. It might occur in the bit that tells the satellite's orientation which way is up. It might occur in the bit that controls the transmission power. It might occur in the bit that tells a critical safety system to activate. A A single bit flip in the wrong place can cause a satellite to malfunction. GPS satellites, which billions of people around the world depend on every single day for navigation, started experiencing degradation. The constellation of GPS satellites orbits Earth, constantly broadcasting timing signals. A receiver on the ground, your smartphone, your car's navigation system, a surveyor's equipment, picks up signals from multiple satellites. By measuring the time it takes for signals to arrive, the receiver calculates its position. The system is staggeringly precise. Modern GPS can know your location to within a few meters. But during the radiation storm, the electronics in the GPS satellites started to malfunction. The atomic clocks that keep precise time began drifting slightly. The transmitters that broadcast the timing signals became less stable. The data being transmitted became corrupted. The accuracy that people take for granted, that ability to know your location to within a few meters, suddenly became less reliable. In some places, GPS accuracy degraded to tens of meters. For civilians, it wasn't a total loss. The system still worked, but it was noticeable. For military applications, for precision agriculture, for financial transactions that rely on GPS timing signals to synchronize computers across the world, for airline navigation, it was significantly more serious. Communications satellites experienced similar issues. A communications satellite is essentially a giant transponder in the sky. It receives a signal from one ground station and retransmits it to another. The signal passes through amplifiers and processing electronics. During the radiation storm, errors in this processing increased. The modulation of the signal, the way information is encoded onto the radio wave, became less stable. Voice signals became noisier, as if someone was listening to a radio broadcast during a thunderstorm. Data transmission became less reliable. Packets of digital information would arrive corrupted. Error correction codes could fix some of the corruption, but during the peak of the storm, the error rate exceeded the correction capability. In some cases, satellite operators proactively reduced their data rates. Instead of transmitting high-definition video, they transmitted standard definition. Instead of transmitting multiple simultaneous calls, they transmitted one. They reduced the quality of service to reduce the impact of radiation-induced errors. It's like a doctor saying to a patient, "We're going to reduce the medication dosage because the side effects are too severe." The satellite operators were essentially asking for less demand on their systems so that the systems could continue to function. Weather satellites, those massive instruments that observe clouds and storms and produce the data that goes into weather forecasts, started showing degradation. The instruments that measure temperature in the atmosphere became less accurate. The instruments that observe wind patterns became less stable. The data streaming from these satellites, data that meteorologists around the world depend on to make weather forecasts, became less reliable. Weather forecasters had to work with degraded data. The uncertainty in their forecasts increased. In some regions, it became noticeably harder to make accurate short-term weather predictions. The economic implications started cascading almost immediately. The loss of GPS accuracy affected agriculture. Farmers using GPS-guided tractors, systems that can plant seeds with meter-level precision, had to switch to less precise guidance. Yields in precision agriculture depend on knowing exactly where to plant and where to apply fertilizer. The degraded GPS accuracy meant less efficient farming. Over the course of a growing season, this adds up to real losses. Airlines flying polar routes, the efficient paths that go over the North Pole on long-distance international flights between North America and Asia, had to make decisions about whether to continue operations or reroute flights. These routes naturally expose crews and passengers to more cosmic radiation because they fly over a region where the magnetosphere is thinner, more porous. The protective bubble of Earth's magnetic field is weaker near the poles. Add in a severe solar radiation storm, and the radiation doses climb significantly. Most airlines continued operations but monitored doses carefully. Flight crews wore radiation dosimeters to track exposure. Dispatchers calculated the radiation dose for each route and made decisions about whether to fly or divert. Some flights were rerouted around the poles, adding hours to the flight time but reducing radiation exposure. The crews received additional radiation exposure during this event. Nothing immediately dangerous, but enough to be concerning for people who fly these routes regularly. Pilots and flight attendants working polar routes accumulate radiation doses over their careers that are higher than the general population. During a severe solar radiation storm, this exposure increases further. The financial impact hit hard as well. Airlines flying longer routes, the ones that require polar navigation to be fuel efficient, were losing money on every flight that had to be rerouted. GPS-dependent industries, delivery companies, precision agriculture, surveying, and construction all experienced losses as the quality of their primary navigation system degraded. It was a pervasive economic impact, not concentrated in one sector but distributed across multiple industries. No single catastrophic failure, but many small failures adding up. The power industry was on high alert. Everyone was thinking about 1989. That was the year that a solar geomagnetic storm knocked out power to the entire province of Quebec, affecting 6 million people. The transformer that steps voltage down from high-power transmission lines to usable levels for homes and businesses are massive pieces of equipment, each one costing hundreds of thousands of dollars. During a severe geomagnetic storm, the changing magnetic field induces currents in these transformers. These currents flow through the windings, and the resistance in the windings causes heating. Multiple transformers were hit by induced currents from the magnetic disturbance. Several of them failed simultaneously. The power system couldn't handle the load redistributed away from the failed transformers. Protective systems kicked in automatically, disconnecting sections of the grid. The whole grid in Quebec collapsed. Power was out across the province. Hospitals ran on backup generators. Subways shut down. Traffic lights stopped working. Office buildings went dark. It was the middle of winter in Canada. People were worried about heating. Businesses lost enormous amounts of money. It took 9 hours to restore power, but during those 9 hours, the disruption was complete and severe. And that was just one province. The 1989 event was a wake-up call for the entire power industry. The power companies learned from that event. They've implemented monitoring systems. They watch the solar activity and the state of Earth's magnetosphere in real time. Satellites monitor the interplanetary magnetic field. Ground stations measure the Earth's magnetic field. When a solar storm is detected and heading toward Earth, the power companies receive warnings. During a severe solar storm, they can take preemptive measures. They can reduce loads on vulnerable sections of the grid. They can disconnect large equipment that might be damaged. Disconnecting a power plant that produces a gigawatt of electricity, temporarily losing that generation capacity, but saving the transformer from being destroyed. It's triage, essentially. You're making the difficult choice between a known harm, losing power generation temporarily, and a potential greater harm, destroying a critical transformer and losing power for months. It's not perfect. A truly catastrophic storm could still cause massive damage, but it's better than being caught completely unprepared. It's the difference between disaster and crisis management. During this recent radiation storm, power companies around the world were essentially in crisis management mode. Teams were standing by in control rooms, watching data streams, ready to make emergency decisions. Some power grids reduced their load. Some disconnected equipment. The situation was serious enough that it was making national news. Network broadcasts interrupted regular programming to report on the solar storm. News anchors explained to viewers that a solar event was happening and that power companies were taking measures to protect the grid. The general public, going about their daily lives, started noticing. They saw news reports. They checked social media and found discussions about the solar storm. Some people felt a sense of unease. What if the power goes out? What if we can't charge our phones? What if the internet goes down? For a brief moment, thousands of people became aware of how dependent our civilization is on reliable electrical power and how vulnerable that power system is to cosmic hazards. Yet despite all this, the lights stayed on for most people. The system held. The infrastructure that humans have built, while certainly vulnerable, proved resilient enough to weather this particular storm. But that doesn't mean we're safe. It means we were lucky. It means the storm was severe, but not quite severe enough to overwhelm the protections that were in place. It means this particular storm, while record-breaking in the modern era, still wasn't quite the absolute worst-case scenario that scientists calculate is theoretically possible. Scientists use mathematical models to estimate what a truly catastrophic event would look like. They input the maximum energy flux, the maximum magnetic field strength, and the maximum potential for transformer failure. The consensus is grim. A solar storm just a few times more powerful than this one. Not an unimaginable event, but one that's perhaps 1,000 times less likely than this one, could cause damage to the power grid that would take months or even years to repair. Transformers that are destroyed can't simply be replaced overnight. They're massive, custom-built pieces of equipment. Lead times for replacement transformers are measured in months. If multiple transformers fail simultaneously across a large region, you don't have months of backup transformer capacity sitting around. In some regions, it could take years to fully restore service. Think about what happens when the power goes out completely. You lose lights, obviously, but you also lose refrigeration. Food spoilage accelerates. Meat, dairy products, frozen foods, all of it spoils within days. Grocery stores can't keep their doors open. Within days, food becomes scarce. You lose water treatment. Modern water systems pump water through distribution networks. Without power, water stops flowing. Within hours, water becomes unsafe. You lose sewage treatment. Waste backs up. Sanitation becomes a critical problem. You lose medical facilities. Hospitals have backup generators, and most large hospitals maintain several days to a week of fuel supply for those generators. But if the grid is down for weeks or months, the fuel supplies for those generators run out. The generators stop running. Operating rooms go dark. Life support systems shut down. You lose transportation systems. Modern vehicles depend on electronic systems for everything: fuel injection, ignition timing, transmission control. Electric vehicles obviously can't charge. Even gasoline vehicles that still use internal combustion engines depend on computers to run. Older vehicles without computers would still work, but they're increasingly rare. Without transportation, supply chains collapse. Goods can't be moved from where they're produced to where they're needed. You lose communications. Cell towers are powered by the grid. The internet depends on powered data centers. Without power, you can't call for help. You can't get information. You can't conduct business. The chaos would be immense. In the pre-industrial era, loss of power might have been merely inconvenient. In the modern era, it would be catastrophic. In a modern city, a power outage lasting more than a week is considered an emergency. An outage lasting months would be a disaster that would dwarf natural disasters like hurricanes or earthquakes in terms of economic cost. And here's the sobering part. We could have avoided many of these vulnerabilities. Technology exists to harden power systems against geomagnetic storms. Transformers can be protected by adding surge protective devices that detect and block induced currents. Backup systems can be installed. If the main grid fails, distributed generation, solar panels, wind turbines, natural gas generators can keep critical systems running. Communication networks can be made redundant. Multiple independent networks so that if one fails, others continue. Hospitals can maintain longer fuel supplies and have better generator systems. But hardening the grid costs money. A comprehensive national program to harden the electrical grid against solar storms would cost tens of billions of dollars. Upgrading transformers, installing protective equipment, building redundancy, it all costs money. And the benefit is speculative. The benefit is protection against events that might happen once every 100 years. Maybe once every 1,000 years. It's a tragedy of commons, in a way. Everyone would benefit from a hardened grid, but the cost is borne by the power companies and their customers, and the benefit is speculative. It's like insurance. You pay for insurance against disaster. Most of the time, you don't need it. Most years, you pay your insurance premium and nothing happens. But when the disaster comes, and statistically, eventually it will, you're glad you paid for the insurance. The challenge with solar storms is that the disaster only comes occasionally, on long timescales measured in decades or longer. Politicians and business leaders are focused on immediate concerns, not hazards that are statistically unlikely to occur during their tenure. That's changing, though slowly. After this radiation storm, conversations are happening again. Engineers are dusting off reports about grid vulnerability that were written decades ago. Policymakers are asking harder questions about readiness. Congressional hearings are being held. Scientists are testifying about the risks. It's the kind of event that doesn't cause immediate disaster but serves as a warning sign. It says, look, this is a real risk. We should take it seriously. And next time, we might not be so lucky. The radiation storm itself provides crucial scientific data. Before this event, we had direct measurements of solar radiation extending back about 50 years. We have satellite data from the beginning of the space age in the 1950s. We know about the severe storms of 1989, 2003, and other notable events. But predictive models are always uncertain, especially when extrapolating beyond the range of direct observations. This event, by surpassing expectations, gave scientists new information about the true limits of solar activity. It pushed the boundary of what we think is possible. The question becomes, how extreme can solar radiation storms actually get? Historically, we have evidence from other sources. Ice cores contain trapped particles called cosmogenic isotopes. When a solar radiation storm hits Earth, it creates additional ionization in the atmosphere, which leads to increased production of isotopes like carbon-14 and beryllium-10. By analyzing ice cores from thousands of years ago, scientists can identify periods when particularly intense radiation storms probably occurred. The evidence suggests that there have been events far more powerful than what we've directly observed in the modern era. The most famous historical event is the Carrington event of 1859. In early September of that year, astronomers observed an enormous solar flare. It was visible without telescopes, a remarkable rarity. The brightness was so intense that the explosion on the sun could be seen in white light against the bright background of the sun itself. The flare was followed by a global magnetic storm of extraordinary intensity. Aurora displays were visible across the entire Earth, even at the equator. Imagine being at the equator, where the aurora is never normally visible, and seeing brilliant curtains of green and red light dancing across the night sky. It would have been absolutely extraordinary. The telegraph systems, which were the high technology of the day, literally caught fire. Operators reported that their equipment sparked spontaneously. Wires became too hot to touch. In some cases, telegraph batteries were disconnected, yet current continued to flow through the wires, driven by the induced currents from the geomagnetic storm. The wires themselves became conductors of the induced currents. The systems experienced what appeared to be self-powered currents flowing through them, even when they weren't connected to their normal power sources. A system designed to operate on a few volts of direct current was suddenly subjected to hundreds or thousands of volts of induced alternating current. The insulation melted. The conductors overheated. The systems failed. If an event of Carrington magnitude happened today, the damage would be almost incomprehensible. Power grids across entire continents could fail. The failure cascade could be so severe that it would take months or even years to fully restore. The economic disruption would be immense. Estimates from researchers at the National Academy of Sciences suggest the economic damage could exceed $1 or $2 trillion. Some projections go even higher, claiming the damage could exceed $3 trillion. For context, that's a significant fraction of the total GDP of the United States. It would be economically devastating, far more damaging than any natural disaster humanity has experienced in modern times. There's a fascinating question about why we haven't experienced a Carrington-level event in the modern era. Is it just luck? Or is there something about the current solar activity that makes such extreme events less likely? Scientists don't have a definitive answer. The statistical probability of such events is low but not zero. Over a span of centuries, such events are virtually certain to occur. The fact that we've had such good luck in the modern era, with our technology dependent on electrical power, is fortunate. But it's not guaranteed to continue. Some evidence suggests that we might be entering a period of unusually high solar activity. Cycle 25, which is the current solar cycle, was initially predicted to be relatively modest. Space weather forecasters expected a cycle similar to the last one, with moderate activity. But early indicators are suggesting something different. The number of sunspots is climbing faster than expected. The strength of the solar magnetic field appears to be increasing. Activity is ramping up more aggressively than the models predicted. Active regions are appearing with increasingly complex magnetic field configurations. Some researchers have speculated that we might be entering a period called the grand solar maximum, a phenomenon where the sun remains unusually active for decades or even centuries. The last clear example was the medieval maximum, which occurred around 900 to 1100 AD. During that period, sunspot counts were extremely high. Solar activity was elevated. Before that, the Maunder minimum from 1645 to 1715 was a period of unusually low solar activity. Very few sunspots were observed. Solar flares were rare. The solar wind was weaker. Interestingly, the Maunder minimum coincided with the Little Ice Age, a time of cooler climate in Earth's history. The connection between solar activity and Earth's climate is complex and not completely understood, but the correlation is suggestive. Some climate scientists have proposed mechanisms linking solar activity to climate. When the sun is less active, there's more cosmic ray ionization in the upper atmosphere. More ionization leads to more cloud formation. More clouds lead to more reflection of sunlight, which cools the planet. When the sun is more active, more cosmic rays are deflected, fewer clouds form, and the planet warms. Other scientists are skeptical of this mechanism, pointing out that the effect size is too small to account for the observed climate changes. The debate continues, but the historical correlations are intriguing. They suggest that solar activity does influence Earth's climate, at least to some degree. If we are indeed entering a grand solar maximum, the implications are significant. We would expect more solar flares, more CMEs, more radiation storms. The statistical probability of experiencing a Carrington-class event becomes much higher. Instead of worrying about a 1 in 100 years probability, we might be looking at a 1 in 30 years or 1 in 20 years probability. Over a century, the chances of experiencing multiple extreme events become substantial. We might experience 2 or 3 Carrington-level events in a century, compared to the historical rate of perhaps 1 event per century or less. This is why the recent radiation storm is so important from a preparedness perspective. It's a data point that helps us understand what the sun is capable of doing. It helps us refine our models. It provides real-world testing of our protective systems and forces us to examine our vulnerabilities. It's a reminder that cosmic hazards are real, quantifiable, and potentially devastating. The measurement and monitoring of solar activity has come a long way since the Carrington event. In 1859, astronomers observed the flare visually with telescopes. They saw the bright outburst in white light. They noted the timing, but they had no quantitative measurements of energy, no data about particle flux, no information about magnetic field strength. Their observations were limited to what they could see and infer from the telegraph failures. Now we have satellites dedicated specifically to observing the sun. The Solar Dynamics Observatory, launched by NASA in 2010, captures high-resolution images of the solar atmosphere in multiple wavelengths. It observes the solar corona, the solar transition region, and the photosphere. It measures magnetic field strength. It watches for flares and tracks their progression. The Parker Solar Probe, launched in 2018, is actually orbiting through the solar corona, measuring conditions there directly. It comes closer to the sun than any spacecraft humanity has ever built. At its closest approaches, it's less than 4 million miles from the solar surface, incredibly close in cosmic terms. SOHO, the Solar and Heliospheric Observatory, a joint mission between NASA and the European Space Agency, has been orbiting at the L1 point between Earth and the Sun for decades. It watches the Sun and monitors CMEs continuously. The moment a CME starts to eject from the Sun, SOHO detects it. Scientists can see the structure of the ejecta, the intensity, the direction. If it's Earth-directed, warnings can be issued. GOES satellites, positioned above the equator in geostationary orbit, continuously measure the radiation environment in near-Earth space. These satellites have instruments that detect solar energetic particles, measure the magnetic field, and track the state of Earth's magnetosphere. All of these assets feed real-time data to space weather forecasting centers. The Space Weather Prediction Center, part of NOAA, operates similarly to how meteorological centers forecast weather, except they're forecasting solar weather. Meteorologists predict rain and thunderstorms using complex mathematical models that simulate the physics of the atmosphere. Space weather forecasters predict solar flares and radiation storms using complex mathematical models that simulate the physics of the sun and the solar wind. It's an imperfect science. We can't predict the precise moment when the sun will flare any more than meteorologists can predict the exact timing of rain weeks in advance. But the forecasters can identify when conditions are favorable. They recognize active regions with high-complexity magnetic fields that are more likely to produce flares. They watch how these regions evolve. When the magnetic field becomes sufficiently stressed and twisted, they issue alerts and watches. They use terminology similar to tornado watches and severe weather watches. A watch means conditions are favorable for an event. A warning means an event is happening now. The recent radiation storm was predicted, at least in its general form. When the CME was observed blasting away from the sun by SOHO, satellites detected it almost immediately. Scientists recognized that it was Earth-directed. Warnings were issued, not just to space agencies but to commercial enterprises as well. Airlines were notified. Power companies were alerted. Satellite operators were prepared. Contingency plans were activated. But the intensity of the event exceeded expectations. The particle fluxes were higher than predicted models suggested. The energies of the particles were higher. The duration of the event was extended. That's the challenge with space weather forecasting. You can predict that something is coming, but the magnitude is harder to pin down. It's like weather forecasting. You can predict that a storm system is coming, but exactly how strong it will be, exactly where it will hit, exactly how much rain it will drop, those are harder to pin down, and even small errors in the forecast can have large consequences for warning and preparation. Let's talk about the actual mechanisms that make radiation storms so dangerous to technology. Spacecraft and satellites operate in an environment where cosmic rays, high-energy particles from space, are constantly present. The magnetic field of Earth and the atmosphere of Earth provide some shielding, but in orbit, the radiation environment is more intense than on the surface. The magnetosphere shields us from the solar wind during quiet times, but during a radiation storm, the shielding becomes less effective, and we're exposed to far more particles. Spacecraft are shielded, but the shielding is never perfect. When a high-energy particle hits shielding material, aluminum, lead, or whatever material surrounds the sensitive electronics, the shielding stops the particle. But the particle's energy doesn't just disappear. It gets transferred to the material. The particle creates a cascade of secondary radiation. Electrons are knocked loose from atoms. Photons are produced. X-rays are generated. In some cases, the shielding actually makes things worse, creating secondary radiation that's more penetrating than the original particle. The internal electronics of satellites are built using transistors so small that they're vulnerable to radiation effects. Modern transistors have dimensions measured in nanometers, billionths of a meter. A human hair is about 100,000 nanometers thick. These transistors are so small that a single high-energy particle passing through one can flip a bit in memory. Modern spacecraft have error correction systems that can detect and fix some of these errors. The most advanced systems use triple redundancy, storing the same bit of information in 3 different locations. If one bit is corrupted, the other 2 can vote and correct it. But during a severe radiation storm, the error rate can exceed the correction capability. Data gets corrupted faster than the error correction can fix it. Computers malfunction. In extreme cases, components can be permanently damaged. The degradation of GPS signals during the radiation storm is a perfect example of how these effects cascade through technology and impact the real world. GPS works by satellites orbiting Earth at an altitude of about 20,000 kilometers. These satellites carry atomic clocks, the most precise timekeeping devices ever created. The clocks are so accurate that they lose or gain only 1 second in millions of years. These satellites constantly broadcast timing signals. The signal carries information about what time it is, according to the satellite's atomic clock, and what the satellite's position is. A receiver on the ground, your smartphone, your car's navigation system, a surveyor's equipment, picks up signals from multiple satellites. The receiver doesn't have an atomic clock. It has a regular quartz oscillator, much less accurate. But by receiving signals from multiple satellites, each signal carrying accurate time from different satellites at different positions, the receiver can do something remarkable. Can measure the time it takes for each signal to arrive. Because the signals travel at the speed of light, the time difference between signals arriving from different satellites tells you about your distance from each satellite. Using the distances from at least 4 satellites, the receiver can calculate its three-dimensional position. This is called trilateration. It's the same principle used in surveying and navigation for centuries, but instead of measuring angles, GPS measures distances using time of arrival information. The system is staggeringly precise. Modern GPS can know your location to within a few meters, sometimes within centimeters with military-grade equipment. It's one of the most remarkable technological achievements of the modern era. But during the radiation storm, the electronics in the GPS satellites started to malfunction. The atomic clocks, so precisely engineered, so carefully calibrated, started experiencing errors. Cosmic ray hits affected the clock circuits. Tiny amounts of charge were created in sensitive regions of the clock, causing the timing to drift slightly. Just a few nanoseconds of error in a satellite's clock translate to dozens of meters of error in the calculated position on the ground. The transmitters that broadcast the timing signals became less stable. The signal strength fluctuated. The data being transmitted became corrupted. The accuracy that billions of people take for granted, that ability to know your location to within a few meters, suddenly became less reliable. In some places, GPS accuracy degraded to tens of meters. For civilians navigating with their smartphones, it wasn't a total catastrophe. The system still worked, you could still get directions, but it was noticeable. Your position on the map jumped around more than usual. Your navigation system occasionally routed you incorrectly. It was annoying but not necessarily dangerous. But for military applications, for precision agriculture, for financial trading systems that rely on GPS timing signals to synchronize transactions across the world, for airline navigation and approach systems, the degradation was significantly more serious. Military systems that depend on centimeter-level GPS accuracy for targeting and navigation found themselves with meter-level or worse accuracy. That's not an acceptable degradation for military operations. Precision agriculture depends on GPS guidance to apply exactly the right amount of fertilizer to exactly the right locations in a field. During the radiation storm, the guidance system's accuracy degraded. Fertilizer was applied in the wrong places. Coverage was uneven. Crop yields suffered. Over the course of a growing season, this adds up to real losses, thousands of dollars per farm. Financial trading systems use GPS time signals to synchronize trades across the world. When different trading centers have slightly different times, small discrepancies can arise. Traders can exploit these discrepancies for profit. The synchronization provided by GPS timing prevents this. When GPS timing became less accurate, the synchronization suffered. Trading systems had to revert to less precise timing sources. The ability to execute certain types of trades was reduced. Communications satellites experienced similar issues. A communications satellite is essentially a giant repeater in the sky. It receives a signal from one ground station and retransmits it to another. Or it receives signals from many ground stations simultaneously and retransmits them to other ground stations. The signal passes through amplifiers and processing electronics. During the radiation storm, errors in this processing increased. Each radiation hit in a sensitive circuit could cause a bit flip, corrupting the data. The modulation of the signal, the way information is encoded onto the radio wave, became less stable. Voice signals became noisier, as if someone was listening to a radio broadcast during a thunderstorm. The quality of calls degraded. Data transmission became less reliable. Packets of digital information would arrive corrupted. Error correction codes built into the data transmission systems could fix some of the corruption, but during the peak of the storm, the error rate exceeded the correction capability. Data got corrupted faster than it could be corrected. In some cases, satellite operators proactively reduced their data rates. Instead of transmitting high-definition video, they transmitted standard definition or even lower quality video. Instead of transmitting multiple simultaneous phone calls through a single satellite transponder, they transmitted just one. They reduced the quality of service to reduce the impact of radiation-induced errors. It's not ideal, customers notice and complain, but it's better than having the system fail completely. Weather satellites, those massive instruments that observe clouds and storms and produce the data that goes into weather forecasts, started showing degradation. The instruments that measure temperature in the atmosphere use radiation sensors. During a radiation storm, the sensors themselves are hit by radiation. The detectors can misinterpret radiation hits as temperature signals. The temperature measurements become corrupted. The instruments that observe wind patterns measure atmospheric motion by tracking features in clouds. Radiation hits in the imaging electronics create artifacts that look like features, confusing the system. The data streaming from these satellites, data that meteorologists around the world depend on to make weather forecasts, became less reliable. Weather forecasters had to work with degraded data. The uncertainty in their forecasts increased. They had less confidence in their predictions. In some regions, it became noticeably harder to make accurate short-term weather predictions. The National Weather Service issued notices about reduced forecast skill due to satellite degradation. Public forecasts became less certain. The recent radiation storm actually served as a valuable test. How did our satellites perform? Which systems showed unexpected vulnerabilities? Which protective measures worked as designed and which failed? These are crucial questions, and the answers we get from analyzing this event will make us better prepared for future storms. Engineers will examine satellite telemetry. They'll identify which components failed and why. They'll design better protection for future satellites. There's also the question of satellite repair and replacement. When a satellite is damaged, it can't be easily fixed. You can't send a technician up to space to repair it. You have to wait until a replacement satellite is ready. Most satellites now have spares in orbit or in development. But if multiple satellites are damaged simultaneously by a radiation storm, the spare capacity might not be sufficient. You might have a gap in coverage while replacement satellites are launched and brought into service. Launching a satellite takes months to years. During the peak of this radiation storm, several satellites experienced anomalies serious enough that they had to be switched to safe mode. In safe mode, a satellite powers down everything non-essential and waits. It doesn't transmit. It doesn't receive. It just tries to survive. Once the radiation storm passes, engineers have to carefully work through procedures to bring the satellite back to normal operation. This takes time. For days or weeks, the satellite is offline. The cascading nature of these failures is what makes radiation storms so concerning. It's not just one system failing. It's many systems degrading simultaneously. Communications degrade. Navigation becomes less accurate. Weather forecasting becomes less reliable. Power systems have to be managed more carefully. The entire technological infrastructure becomes more fragile, more prone to failures, more stressed. And yet, despite all this, the systems held. No catastrophic failures. No cascading blackouts. No complete loss of any critical service. The infrastructure proved more resilient than the worst-case fears. But that's no guarantee for next time. That's no guarantee that the next storm won't be a bit stronger, pushing systems past their breaking point. This is why scientists take solar storms seriously. This is why space agencies invest in monitoring the sun. This is why power companies maintain watch over space weather data. The next major storm could be worse. The next major storm could be the one that causes significant damage. And there's no way to prevent solar storms. We can't go up to the sun and ask it to please stop producing flares. We can only prepare ourselves for the inevitable and hope that when the next major event occurs, we're ready. The science of understanding these events has evolved tremendously over recent decades. We've gone from visual observations by astronomers to continuous satellite monitoring, real-time particle detection, and sophisticated computer models. We understand the physics of the sun far better than we did even 50 years ago. We know how magnetic fields can store energy and release it catastrophically. We know how shock waves accelerate particles. We know how the solar wind interacts with Earth's magnetosphere. But there's still much we don't understand. We can't perfectly predict where a flare will occur. We can't perfectly predict how powerful it will be. We can't perfectly predict how a CME will interact with Earth's magnetosphere. These uncertainties are because the Sun is fundamentally a chaotic system. Chaos, in the technical sense, means that tiny differences in initial conditions lead to vastly different outcomes. We can't measure the Sun's state with infinite precision, so we can't predict the Sun's behavior with infinite precision. This is actually comforting in a way. It means that no matter how advanced our science becomes, there will always be surprise and unpredictability in the universe. It means we can never achieve complete control over our environment. It means we have to maintain a degree of humility about our place in the cosmos. The universe will always be capable of surprising us. One of the most profound things about being alive in this universe is that you don't have to understand quantum mechanics to know that something fundamental is missing from our picture of reality. You feel gravity every single second of your existence. Right now, as you sit there watching this video, you're being pulled toward the center of the Earth with a force that is constant, relentless, and utterly invisible. But here's the thing that absolutely haunts physicists. We don't actually know what gravity is. Not really. We have equations that describe how it behaves. We have theories that predict its effects with astonishing precision. But what gravity actually is, at the most fundamental level, remains one of the deepest mysteries in all of science. I'm Neil deGrasse Tyson, and I've spent decades looking up at the cosmos, trying to understand our place in this vast universe. And the more I've learned about physics, the more I've realized that gravity, this seemingly simple force that keeps us grounded, that keeps the moon orbiting Earth, that keeps the Earth orbiting the sun, that holds together entire galaxies, might be the most mysterious phenomenon in all of science. It's the invisible hand that shapes the cosmos. It's the architect of galaxies. It's the sculptor of stars. And we're only just beginning to understand how little we actually know about it. Today, I want to take you on a journey through one of the deepest mysteries in physics. We're going to explore what gravity really is, where it comes from, how it works at the smallest and largest scales of the universe, and most importantly, we're going to examine how understanding gravity might fundamentally break our current understanding of the universe and force us to rebuild physics from the ground up. This is not a simple story. It's a story full of contradictions, mysteries, and questions that have haunted the greatest minds of our time. When Isaac Newton formulated his law of universal gravitation in 1687, he did something truly remarkable. He took observations of falling apples, planetary motions, tides, and the orbits of celestial bodies, and he unified them all under one mathematical principle. His law states that every mass in the universe attracts every other mass with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between them. In mathematical form, it's elegant. In practical application, it's powerful. For more than 2 centuries, it worked beautifully. Scientists used Newton's mathematics to predict planetary positions with astonishing accuracy. They calculated the trajectories of comets. They determined the orbits of moons. They understood the dance of binary stars spiraling toward each other in the cosmic dark. Newton's theory of gravity was so successful that it became the foundation of classical mechanics. It allowed us to understand the motions of the heavens and the earth. It made possible the age of celestial mechanics. And yet, Newton himself admitted something remarkable. He had no idea how gravity actually works. He wrote, and I'm paraphrasing here, "It is inconceivable that inanimate brute matter should, without the mediation of something else which is not material, operate upon and affect other matter without mutual contact." In other words, Newton looked at his own equations and basically said, "I have no idea how the Earth reaches out across empty space and pulls on you. I just know that it does." This admission from one of the greatest minds in history reveals something profound. Even genius has its limits when confronted with the deepest mysteries of nature. That unsolved mystery haunted physicists for centuries. How does gravity propagate through empty space? What is the mechanism? How can 2 objects separated by the vast vacuum of space exert forces on each other without anything connecting them? These questions seemed almost metaphysical. They seem to violate the principle that something cannot act where it is not. And yet, gravity clearly does act across empty space. The sun's gravity reaches across 93 million miles of empty space to hold the Earth in orbit. And billions of years ago, when the sun was born, it wasn't close to the Earth. It was a collapsing cloud of gas and dust. Gravity acted across that entire cloud, pulling it together, concentrating it, heating it, until nuclear fusion ignited in its core. Then, in 1915, Albert Einstein revolutionized our understanding of gravity with his theory of general relativity. And instead of thinking of gravity as a force, Newton's invisible hand pulling objects together, Einstein showed us something far more profound and far more strange. He showed us that gravity is not a force at all. It's geometry. It's the shape of space-time itself. Imagine space-time as a rubber sheet stretched out in all directions. It's smooth, it's flexible, and it extends infinitely. Now place a bowling ball in the center of that sheet. The ball doesn't push down on the sheet with some mysterious force. Instead, its mass warps the very fabric of space-time around it. The sheet curves and bends. It develops a depression, a valley around the ball. Now, when you roll a marble across that curved sheet, it doesn't travel in a straight line like it would on a flat surface. It curves toward the bowling ball, following the contours of the warped space-time. That curved path is what we perceive as gravity. The marble isn't being pulled by an invisible force. It's following the geometry of the space it's moving through. This insight was revolutionary. Gravity wasn't action at a distance anymore. It wasn't some mysterious force propagating through empty space. It was the geometry of the universe itself responding to the presence of mass and energy. And the mathematics was so elegant, so powerful, so beautiful that it made predictions Newton's theory never could. It explained the precession of Mercury's orbit with perfect accuracy. Newton's theory said Mercury should orbit the sun in a perfect ellipse, but Mercury's orbit actually precesses. The perihelion, the point of closest approach to the sun, shifts slightly with each orbit. Einstein's equations explained this shift exactly, predicted that light would bend around massive objects. This was counterintuitive. Light was supposed to be massless. How could a massless thing be affected by gravity? But Einstein's equations said that gravity bends spacetime, and light follows the curves of spacetime. So light should bend around massive objects. When Arthur Eddington observed a solar eclipse in 1919, he positioned telescopes to photograph stars near the sun's edge. According to Einstein's predictions, the sun's gravity should bend the starlight, making the stars appear to shift from their normal positions. When Eddington analyzed the photographs, he found exactly this shift. The starlight had bent around the sun just as Einstein predicted. In one moment, Einstein went from being a brilliant but relatively unknown theoretical physicist to being a world-famous figure. The headline in the Times of London read something like, "Revolution in Science, New Theory of the Universe." And it was true. Einstein had revolutionized our understanding of gravity and spacetime. But here's where things get really interesting, and where I want you to pay close attention, because this is where gravity starts to reveal cracks in the foundation of physics. This is where gravity begins to threaten to break the universe. In the 1960s and 1970s, a brilliant physicist named Stephen Hawking made a discovery that seemed impossible. He combined Einstein's gravity with quantum mechanics, and what emerged was something that shattered our understanding of black holes forever. Black holes, Einstein's theory predicted, should be completely black. Once something crosses the event horizon, the point of no return, nothing can escape, not even light. But Hawking showed that black holes are not completely black. They emit radiation, they have a temperature, they have entropy, and remarkably, they can evaporate completely. This Hawking radiation, as it came to be known, was the first significant hint that gravity and quantum mechanics are fundamentally incompatible at the deepest levels. Here's why. Quantum mechanics says that at the smallest scales, at the Planck scale, about 10 to the minus 35 meters, which is almost incomprehensibly small, reality becomes probabilistic. Particles don't have definite positions and momenta. They exist in a cloud of probability. They can be in superposition in multiple states at once until measured. But Einstein's gravity, his general relativity, describes a smooth, continuous spacetime. These two pillars of modern physics tell completely different stories about how reality works. At the event horizon of a black hole, where gravity becomes infinitely strong, quantum effects become crucially important, and these two theories collide head-on. Something has to give. Scientists have been trying for decades, centuries really if you count from Newton onward, to reconcile these two incompatible theories. Some propose string theory, which suggests that fundamental particles aren't points but tiny vibrating strings. Others suggest loop quantum gravity, where spacetime itself is quantized into discrete loops. Still others propose that spacetime is an illusion, emerging from something more fundamental, perhaps from pure information, perhaps from quantum entanglement, perhaps from something we haven't even conceived of yet. But here's the thing, we don't know which, if any, of these approaches is correct. And that's the first hint that gravity might allow us to break the universe, by revealing the deepest contradictions in our understanding of nature. But wait, there's more. Much more. In 1998, astronomers Saul Perlmutter, Brian Schmidt, and Adam Rees made an observation that completely blindsided the physics community. They were studying type Ia supernovae, these brilliant cosmic explosions that occur when a white dwarf star, the remnant of a sun-like star, pulls material from a companion star. Type Ia supernovae have a peculiar property. They have roughly the same intrinsic brightness, the same absolute magnitude. This makes them excellent, standard candles for measuring cosmic distances. If you know how bright something actually is intrinsically, and you measure how bright it appears from Earth, you can calculate how far away it is. So Perlmutter, Schmidt, and Rees measured the distances to dozens of these supernovae, going back billions of years into cosmic history. Using telescopes to observe incredibly distant galaxies, they measured the light from supernovae that exploded billions of years ago. And here's what they expected to find. The universe is expanding. We know that from Hubble's observations a century earlier, but they expected the expansion to be slowing down. Gravity, after all, is attractive. The gravitational pull of all the matter in the universe, all the stars, all the planets, all the gas, all the dark matter, should be pulling things back together. It should be decelerating the cosmic expansion. The universe should be expanding, but slowing down over time, like a ball thrown upward against gravity. But that's not what they found. The supernovae were farther away than they expected. The universe wasn't just expanding, it was accelerating. The expansion was speeding up. It was as if someone had pressed the cosmic gas pedal. The universe was expanding faster and faster. This was so shocking that when these results were first presented, many physicists thought there must be a mistake. There had to be systematic errors in the observations. There had to be dust blocking their view. There had to be something they hadn't accounted for. But the results held up. The observations were repeated. Different teams confirmed the findings. The evidence became overwhelming. The universe is accelerating. And that means something is pushing the galaxies apart with an ever-increasing force. Something is working against gravity. Something is causing the cosmic expansion to speed up. And we have absolutely no idea what it is. We call this mysterious force dark energy. And it comprises about 68% of the entire universe. 68%. Think about that for a moment. Let that sink in. Everything you can see, every star, every galaxy, every supernova, every comet, every asteroid, every planet, every speck of dust, even you, all of that makes up only 32% of the universe's total energy content. The visible universe, everything that emits light or reflects light, everything made of atoms like the ones in your body, comprises only about 5% of the universe. The vast majority of matter is dark. We can't see it, we can't touch it, we can't observe it directly. We only know it exists because of its gravitational effects. And then there's dark energy, which comprises 68% of everything. We're rounding errors in the cosmic budget. We're like a drop of water in an ocean that is itself immeasurably vaster than we can conceive. The universe is driven primarily by something we don't comprehend. We don't know what it is. We don't know where it comes from. We don't know if it's constant or if it varies over time. And this should terrify and humble every physicist on Earth. We've built a magnificent edifice of understanding about gravity and the universe, and it turns out we're missing the dominant component. Now, dark energy presents a fundamental problem to gravity as we understand it. Einstein's equations relate the geometry of spacetime to the distribution of matter and energy. If you know where the matter and energy are, you can solve Einstein's equations and find the curvature of spacetime. If you know the curvature of spacetime, you can predict how objects will move. But dark energy is smooth. It's not concentrated in galaxies or clusters of galaxies. It's distributed uniformly throughout space. And it has a really weird property. Its energy density doesn't change as the universe expands. Let me say that again because it's important. In normal physics, when something expands, it gets diluted. If you have a gas in a container and you expand the container, the density of the gas goes down. But dark energy doesn't work that way. As the universe expands and becomes larger, dark energy doesn't get diluted. In fact, it seems to get more powerful. The expansion accelerates faster and faster. This shouldn't be possible, but that's what we observe. Some physicists propose that dark energy is simply the cosmological constant, a fudge factor that Einstein himself had introduced into his equations back in 1917, then later called his greatest blunder. The cosmological constant is just a form of energy inherent to spacetime itself, present everywhere and forever, unchanging throughout the history of the universe. But this creates an enormous problem called the cosmological constant problem, one of the biggest unsolved mysteries in physics. It's so fundamental, so troubling, that it might be the key to unlocking a whole new level of physics. Quantum field theory, when applied to the vacuum, empty space, predicts that the vacuum should have enormous energy density. The calculations suggest it should be about 10 to the 120 power times larger than what we actually observe. That's 1 followed by 120 zeros. To give you a sense of scale, there are only about 10 to the 80 atoms in the observable universe. There are more zeros in the predicted vacuum energy than there are atoms in the entire universe. It's not like being off by a little bit. It's not being off by a factor of 1,000 or a million or a billion. It's off by 10 to the 120. It's the most catastrophic disagreement between theory and observation in the entire history of science. It's so bad that physicists have mostly stopped talking about it in public because it makes us sound crazy. But privately, it haunts them. It haunts me. This discrepancy suggests that either quantum field theory is fundamentally wrong at some level, or general relativity breaks down at the scales we're probing, or both are incomplete, or something entirely different is going on that we haven't even conceived of yet. And this is the second way gravity threatens to break the universe, by revealing fundamental contradictions at the largest scales. The universe is not just a bigger version of what we've tested in laboratories and with satellites. It operates by rules we don't yet understand. Let me take you even deeper into this mystery. Let's go back to the smallest scales, because there's another profound mystery brewing there that could transform everything we know. In recent years, physicists have become increasingly interested in what happens at the singularities of black holes. The singularity is that point of infinite density at the center of a black hole, where all the matter has been compressed to an infinitely small volume, where the curvature of spacetime becomes infinite. It's where general relativity breaks down completely. The equations blow up. You get infinities everywhere. And infinities in physics are usually a sign that you're pushing your theory beyond its domain of validity. It's like trying to use Newton's laws to describe the collision of two particles at the speed of light. The equations don't work. They give nonsensical answers. Now, according to Einstein's theory, once you cross the event horizon of a black hole, you're doomed. Your fate is sealed. Nothing can escape. Not even light. Not even you. Time and space swap roles inside the event horizon. You can move toward the future, and the future points toward the singularity. You can no longer escape the singularity any more than you can escape tomorrow. Your inevitable future is the singularity. But if gravity, as Einstein described it, is all there is, then that singularity is a real physical thing. It's a place where our physics completely fails. It's a place where the universe breaks. But what if gravity doesn't have the final word? What if, at the smallest scales, at the Planck scale, quantum effects become so important that they dominate? What if, as you approach the singularity, quantum gravity effects become so strong that they prevent the singularity from ever forming? This is speculative, absolutely speculative, But some physicists have proposed models where black holes don't actually contain true singularities. Instead, quantum effects might create a firewall, a region of incredibly intense energy at the event horizon. Or perhaps quantum gravity effects create a bounce at a Planck scale radius, bouncing matter back outward before it can form a singularity. Or perhaps the black hole evaporates via Hawking radiation without ever developing a true singularity. If this is true, if quantum gravity naturally prevents singularities from forming, then it means that gravity, combined with quantum mechanics, naturally prevents the universe from breaking, prevents infinities from appearing. It prevents the mathematical structure of spacetime from developing true singularities. It regularizes itself. That's beautiful. That's elegant. That's what we'd hope to find in a truly fundamental theory. But it also means we need a theory of quantum gravity to understand black holes properly. And we don't have one yet. Now, let's talk about something that really keeps me awake at night. The possibility that gravity itself might be emergent. That spacetime and gravity might not be fundamental at all. Over the past 2 decades, a growing number of physicists have entertained a radical idea. And when I say radical, I mean it challenges the very foundation of how we think about physics. What if spacetime and gravity are not fundamental? What if they emerge from something more basic, something we haven't discovered yet? This isn't the ravings of pseudoscientists. This is being explored by serious physicists at serious institutions. This idea is inspired, in part, by the ADS/CFT correspondence discovered by one Meldesena in 1997. ADS stands for anti-de Sitter space, a particular type of curved spacetime. CFT stands for conformal field theory, a quantum field theory without gravity. Meldesena discovered something astonishing. A gravitational theory in anti-de Sitter space is mathematically equivalent to a quantum field theory in a lower-dimensional space without gravity. It's like a hologram. The 3-dimensional gravitational theory is like a hologram of the 2-dimensional quantum field theory. All the information in the gravitational theory is encoded in the lower-dimensional field theory. This correspondence is not just a mathematical curiosity. It suggests that gravity might be emergent. It suggests that if you have the right quantum field theory living on the boundary of spacetime, gravity emerges in the bulk. It's like the way temperature emerges from the motion of molecules. Individual molecules don't have temperature. But when you have trillions of molecules moving around, bouncing off each other, you can define a temperature that describes the average kinetic energy. Similarly, gravity might emerge from quantum information or quantum entanglement. If gravity is emergent, it means that all the weird things we associate with gravity, black holes, singularities, event horizons, curved spacetime, might not be fundamental aspects of reality. They might be collective phenomena. They might arise from something at a deeper level that we haven't yet discovered. This is like understanding fluid dynamics. Fluid dynamics seems to be a fundamental description of how liquids and gases behave. Water flows, air currents swirl, things float and sink. But at a deeper level, fluid dynamics emerges from the motions of zillions of individual molecules. Individual molecules don't flow. They bounce around randomly, but collectively, they create the phenomenon we call fluid flow. Similarly, gravity might emerge from something at a deeper level. Spacetime might not be fundamental. It might be an emergent phenomenon. And that would mean our understanding of gravity is like our understanding of temperature before we knew about atoms. We knew temperature was real. We could measure it. It was incredibly useful. But we didn't understand it was really just the average kinetic energy of zillions of particles. We thought it was a fundamental property of matter. But it wasn't. Similarly, gravity might be real and useful and predictive, but it might ultimately be a statistical phenomenon arising from something far more fundamental. This is speculative, absolutely, but if it's true, it has profound implications. It suggests that the next revolution in physics won't be modifying Einstein's equations. It will be realizing that Einstein's equations are an effective description of something deeper, and that's a completely different kind of revolution. Let me introduce you to another mystery that connects gravity to the very fabric of existence: the nature of time itself. In Einstein's relativity, time is not absolute. It's not the same everywhere. It's relative. It flows at different rates depending on gravity and velocity. This is not just theoretical speculation. We've measured it. We've tested it. Atomic clocks on airplanes tick at slightly different rates than atomic clocks on the ground due to the speed of the airplane. More dramatically, atomic clocks on satellites tick at different rates than atomic clocks on the surface of the Earth. GPS satellites wouldn't work without relativistic corrections. If you didn't account for the fact that time runs faster in space, farther from the Earth's gravity well, than it does on the surface of the Earth, GPS would give you your location wrong by kilometers within hours. Time actually runs faster in space because gravity is weaker there. And near black holes, time slows to a crawl. At the event horizon of a black hole, time stands still. An external observer would see an infalling object asymptotically approach the event horizon, moving slower and slower, its light becoming more and more redshifted, until it seems to freeze at the horizon. But to the infalling object, it would cross the event horizon in finite time and hit the singularity. But here's where it gets really strange and really problematic. Physics at the quantum level operates in a very different way. In quantum mechanics, there's a fundamental symmetry called time reversal symmetry. Many quantum processes look the same whether time flows forward or backward. If you recorded a quantum interaction at the atomic scale and played it backward, you wouldn't be able to tell the difference. It would look just as valid. But gravity breaks this symmetry spectacularly. The universe evolves in one direction through time. Entropy increases. We age. We move from the past to the future. Sti. Black holes form. Galaxies collide. These processes are fundamentally asymmetric in time. You don't see stars unburning. You don't see black holes unforming. You don't see galaxies uncolliding. This asymmetry is called the arrow of time. Now, here's the mystery that keeps physicists up at night. Where does this arrow come from? What in the laws of physics creates the distinction between past and future? The microscopic laws, both quantum mechanical and gravitational, are largely time reversible. But our macroscopic experience is not. The universe evolves from low entropy to high entropy, from order to disorder, from structure to chaos, and nobody really understands why. Some physicists argue that it has to do with the initial conditions of the Big Bang, which was in an extraordinarily low entropy state. The Big Bang started in a very ordered, structured state. As time went on, entropy increased, disorder increased. But why was the Big Bang in such a low entropy state? Why didn't it start in maximum entropy? Why was it special? And what role does gravity play in that? This is profound because it suggests that the arrow of time might be connected to gravity. The initial low entropy of the Big Bang might have been determined by gravity somehow. The evolution of the universe under gravity might naturally increase entropy. And that would mean gravity is not just the geometry of spacetime. It's also the arrow of time. Roger Penrose, one of the greatest living physicists, has proposed that this time asymmetry might be fundamental to how gravity works. He's suggested that gravity, over cosmological timescales, actually drives the universe toward ever-increasing entropy. And he's proposed a model called conformal cyclic cosmology, or CCC, where the universe goes through infinite cycles, each one being the infinite future of the previous one. In each cycle, gravity is so strong and spacetime becomes so vast that the very distinction between the infinite future and a new beginning becomes meaningless. The infinite past of one universe is identical to the infinite future of another. Time is cyclical, but at a scale so vast that within each cycle it appears linear. If Penrose is right, if his conformal cyclic cosmology is the true description of the universe, then gravity is not just responsible for orbits and tides. It's not just the geometry of spacetime. It's responsible for the fundamental direction of time itself. It's responsible for the distinction between past and future. And that would mean gravity is even more fundamental, even more central to existence than we've ever imagined. It would mean that the nature of time, your experience of moving from past to future, your memories of the past, your hopes for the future, is ultimately a consequence of gravity's influence on the structure of spacetime. It would mean that without gravity, there would be no time. There would be no before and after. There would be no change. Now, let's consider one more mystery that brings all of these threads together: the black hole information paradox. In the 1970s, Stephen Hawking made that astonishing discovery that black holes emit radiation. And from that radiation spectrum, you can extract the temperature of the black hole, which is related to its mass. The smaller the black hole, the hotter it is. And the hotter something is, the faster it radiates energy. This means smaller black holes evaporate faster. Eventually, any black hole will evaporate completely, in a process that could take longer than the current age of the universe, 10 billion years for stellar mass black holes. But for tiny black holes, it could happen in microseconds. But here's the problem, and it's a deep one that cuts right to the heart of the incompatibility between gravity and quantum mechanics. When a black hole evaporates via Hawking radiation, where does all the information that fell into the black hole go? Quantum mechanics, one of the pillars of modern physics, says information can't be destroyed. It has to go somewhere. It has to be encoded in the pattern of the radiation that emerges. But when you do the calculations, you find that the Hawking radiation is completely thermal. It's random. It has no information encoded in it. Every black hole that forms from the same initial conditions and evaporates will produce essentially the same radiation. There's no way to distinguish them. There's no way to recover the information about what fell in. If you throw a book into a black hole, that book, all the information in it, seems to be lost forever. If you throw a different book into an identical black hole, it would evaporate and produce indistinguishable radiation. This violates the fundamental principle of quantum mechanics that information is conserved. This is the black hole information paradox, and it's a direct contradiction between gravity and quantum mechanics. Einstein's general relativity says that information can be lost in a black hole. Quantum mechanics says it can't. Both can't be right. Something has to give. And resolving this paradox might require a completely new understanding of gravity. Some physicists, like Juan Meldacena and others, have argued that the information isn't really lost. It's scrambled. It's in the radiation, but in such a way that it's impossible to extract with any practical measurement. The information is there, but it's so thoroughly mixed up that you'd need to analyze the Hawking radiation in impossible ways to extract it. Others argue that gravity must be modified near black holes to prevent the information loss. Perhaps gravity becomes stronger or weaker near the singularity in a way that allows information to escape. And some argue that the paradox is telling us that gravity, at the most fundamental level, is not a continuous field but something more discrete and quantum in nature. The resolution of this paradox could fundamentally reshape our understanding of gravity. It could reveal that gravity at the Planck scale is quantized like all other forces. It could show that space-time has a discrete structure, like a lattice of quantum events. It could reveal that space-time is not continuous but made up of discrete chunks. Or it could reveal something we haven't even thought of yet. Now, I want to step back and talk about what all of these mysteries mean for the future of physics. Because I think we're at a turning point. We're at a crucial moment in human history where our understanding of the universe is about to undergo a fundamental transformation. Gravity is the only fundamental force we haven't successfully quantized. Electromagnetism, the weak nuclear force, and the strong nuclear force have all been incorporated into quantum field theories. We understand these forces at both quantum scales and large scales. But gravity has resisted every attempt. And I don't think that's an accident. I think it's telling us something profound. There are several possibilities for what that something might be. First, gravity might be fundamentally different from the other forces. Maybe quantizing it requires a completely different approach than what worked for the other forces. The weak and strong nuclear forces, electromagnetic force, they all operate in the framework of quantum field theory. They're all mediated by particles. But gravity doesn't fit nicely into this framework. Maybe we need a new framework entirely. Second, maybe spacetime itself is not the right framework. Maybe the very concept of spacetime, a four-dimensional continuum with 3 spatial dimensions and 1 temporal dimension, is not fundamental. Maybe it's an approximation. Maybe at the deepest level, reality is not a spacetime at all. Maybe it's something else. Maybe it's information. Maybe it's patterns of quantum entanglement. Maybe it's pure mathematics. But whatever it is, it's not spacetime. Third, maybe there are additional dimensions that we don't know about. String theory predicts 10 or 11 dimensions depending on the version. Maybe we live in a world with many more dimensions than we perceive. Maybe gravity is actually strong in those extra dimensions, and what we perceive as the weakness of gravity on large scales, the fact that gravity is so much weaker than the other forces, is because it's spreading into dimensions we can't see. Most of the gravitational force is in the extra dimensions. What we see is just the spillover. Fourth, maybe gravity is an illusion. Maybe it's not even a real force. Maybe it's an emergent phenomenon arising from something at a deeper level, like the entanglement of quantum information. This last possibility sounds crazy, but serious physicists are exploring it. It's called entropic gravity, the idea that gravity is not fundamental but is a consequence of entropy maximization in quantum systems. The universe, in a sense, tries to maximize entropy, and gravity emerges as the manifestation of this principle. Fifth, maybe time itself is not fundamental. Maybe the past, present, and future all exist equally. Maybe time is like space, you can move backward in space, and in the same way, the universe exists in a static, unchanging block where past, present, and future all coexist. This is called block universe or eternalism, and it's a serious position in philosophy of physics. If time is not fundamental, if all times exist equally, then the evolution of the universe is also not fundamental. It's just the structure of the four-dimensional space-time. Any of these possibilities would represent a revolution in physics. And I suspect that understanding how to resolve the contradictions within gravity, how to reconcile it with quantum mechanics, how to explain dark energy, how to resolve black hole information paradoxes, how to understand time, will require embracing one or more of these radical ideas. But here's what I find most fascinating. These mysteries of gravity might be the gateway to understanding something even deeper about the nature of existence itself. Let me explain what I mean. In recent decades, physicists have become increasingly interested in the role of quantum entanglement in the structure of spacetime. Entanglement is that phenomenon Einstein called spooky action at a distance, where two quantum particles can be correlated in such a way that measuring one instantly affects the state of the other, no matter how far apart they are. It's real. We've tested it extensively. It's been confirmed over and over. And it's one of the most counterintuitive features of quantum mechanics. When two particles are entangled, they share a quantum state. They're connected in a fundamental way. And what's remarkable is that this connection is not mediated by any signal traveling between them. It's instantaneous. It's as if the particles are part of a single quantum system, no matter how far apart they are. This seems to violate relativity, which says nothing travels faster than light. But it doesn't actually violate relativity because you can't use entanglement to send information faster than light. The correlations only become apparent after you communicate the measurement results, which travels at or below the speed of light. Now, some physicists, including those working on the ADS/CFT correspondence and related holographic theories, have begun to suspect that entanglement is not just a quantum phenomenon. It might actually be responsible for creating spacetime itself. The idea is that spacetime emerges from a web of entangled quantum information. Imagine a vast network of qubits, the quantum equivalent of bits. These qubits are entangled in a complex pattern. The pattern of entanglement determines the structure of spacetime. Regions that are highly entangled are close together in spacetime. Regions that are weakly entangled or not entangled are far apart. If two regions become disentangled, spacetime develops structures that separate them. Wormholes form, boundaries appear. As the universe evolves, as interactions occur between qubits, the pattern of entanglement changes. With it, the geometry of spacetime itself changes. Stars form, galaxies form, black holes form, universes might even split. If this is true, and this is still highly speculative, it's on the frontier of theoretical physics, then gravity is not a force at all. It's the geometry of spacetime, which emerges from the pattern of entanglement in the quantum state of the universe. This would mean that understanding gravity at the deepest level requires understanding how entanglement gives rise to spacetime. It would mean that gravity and entanglement are two faces of the same phenomenon. And that would represent a complete unification of quantum mechanics and gravity, but at the cost of completely reconceiving both. This is where I think physics is headed. Not toward a modification of general relativity or quantum mechanics, but towards something deeper that encompasses both. A theory where space-time, gravity, and quantum entanglement are all understood as different aspects of the same underlying reality. A theory where what we call gravity is really the structure of a vast network of entangled quantum information, where what we call space-time is the geometrical manifestation of quantum correlations. Now, let's talk about the implications of these ideas for actually breaking the universe, as your title suggests. What does it mean to break the universe? I think it means to discover something that violates the fundamental laws of physics as we understand them. It means to find the limit of our understanding and push beyond it. It means to realize that our current framework is incomplete or incorrect. And I believe that gravity is the key to doing that. Gravity is the wall we've hit. It's the place where our understanding breaks. And breaking through that wall might lead to a completely new understanding of reality. First, understanding gravity properly will likely resolve the contradiction between quantum mechanics and general relativity. This alone would be earth-shaking. It would give us a unified theory of all the forces and all of physics. We've already unified electromagnetism and the weak nuclear force into electroweak theory. The strong nuclear force is described by quantum chromodynamics. But gravity stands apart. It's the odd one out. If we could incorporate gravity into a quantum framework, or if we could understand how quantum mechanics emerges from gravity, we would have a unified theory of everything. We would have a framework that describes all the forces, all the particles, all the phenomena we observe, from the smallest subatomic scales to the largest cosmological scales. That's profound. But more than that, it would mean we understand the deepest level of reality. We would have a theory of quantum gravity that explains what happens at black hole singularities, what happens at the moment of the Big Bang, when gravity was infinitely strong and the universe was infinitely hot. We would understand the origin of the universe itself. Or perhaps we would realize that the universe doesn't have an origin in the conventional sense. Perhaps it's eternal. Perhaps it's cyclical. But whatever it is, we would understand it. Second, understanding gravity might explain dark energy. Maybe dark energy is not a mysterious form of energy at all. Maybe it's a sign that gravity behaves differently at cosmological scales. Maybe Einstein's equations need to be modified. Maybe gravity becomes repulsive on the largest scales. Or maybe gravity is weaker than we think on those scales, and what we interpret as dark energy is actually a sign that Einstein's theory breaks down for cosmological geometry. There are alternative theories of gravity that attempt to explain cosmic acceleration without dark energy. They modify general relativity slightly, adding extra terms to Einstein's equations that become significant at large scales. These modified gravity theories make different predictions for structure formation and the growth of galaxies, and we're testing them against observations. If we can explain dark energy, we'll have explained 68% of the universe. That's enormous. We'll have solved one of the deepest mysteries of cosmology. Third, understanding gravity might reveal whether the universe is eternal or whether it had a beginning. And if it had a beginning, it might tell us what came before, which sounds nonsensical until you realize that gravity, according to some theories, creates time itself. Stephen Hawking and others have proposed that the universe might be self-contained in spacetime. The boundary of spacetime is at the Big Bang, which is at infinite density and infinite temperature. But in quantum gravity, you're supposed to integrate over all possible spacetimes, not just classical spacetimes. Hawking proposed that quantum gravity naturally selects spacetimes without boundaries. And spacetime without a boundary means there's no singularity. There's no moment of creation. The universe just is. It always was. If this is true, asking what came before the Big Bang is like asking what's north of the North Pole. It's a meaningless question. There is no before. Time itself begins at the Big Bang. But understanding why it's meaningless, understanding the quantum gravity principles that lead to a no-boundary universe would be profound. It would reshape our understanding of existence itself. Fourth, understanding gravity might transform our understanding of consciousness and the nature of mind. This sounds even more far-fetched, and I want to be careful here because this is deeply speculative. But some physicists and philosophers have speculated about the connection between the collapse of quantum wave functions, when a superposition of possibilities becomes a definite reality, and the moment of conscious observation. If consciousness is somehow involved in quantum collapse, and if gravity influences quantum behavior, then gravity might be connected to consciousness. Now, most physicists would dismiss this outright. The hard problem of consciousness, why and how physical processes give rise to subjective experience, is a notoriously difficult philosophical problem. And connecting it to gravity seems like a stretch. But a few serious researchers, including some Nobel laureates like Penrose, have thought deeply about this. And they've proposed models where quantum effects in the brain, particularly in microtubules within neurons, might be relevant to consciousness. Penrose has proposed that quantum gravity effects in the brain might be responsible for consciousness. That consciousness is a quantum gravity phenomenon. This is deeply speculative. I want to emphasize that we don't have evidence that consciousness is connected to gravity. But understanding gravity might shed light on this mystery too. It might force us to revise our understanding of consciousness. But perhaps most fundamentally, understanding gravity means understanding the nature of reality itself. Because gravity, Einstein taught us, is not a force that exists in spacetime. Gravity is the structure of spacetime. To understand gravity is to understand the fabric from which all of existence is woven. It's to answer the question, what is space? What is time? Why does space have 3 dimensions and not 4 or 2? Why does time flow in one direction? Why does the universe have the properties it has? These are the deepest questions in physics and philosophy, and gravity is the key to answering them. Now, I want to be clear about something. We might never fully resolve all these mysteries. Physics has always been about pushing back the frontiers of the unknown, but there are always new frontiers beyond. As we solve problems, we discover new ones. The history of physics is not a march toward a final theory. It's a spiral. We get closer and closer to understanding, but the deeper we dig, the more we realize how much deeper the mystery goes. And I think this is how it will always be. We'll make progress. We'll understand more. But the universe will always have secrets. But that's not a failure of physics. That's what makes it beautiful. That's what makes it alive. That's what makes it worth doing. Every time we understand something, the universe opens up new doors of mystery. We solve one puzzle and discover 3 new ones. And gravity is the deepest mystery of all, because it's the structure of existence itself. Let me conclude with something that I think connects all of these threads and points toward where the physics of the future might lead us. We live in a universe that is fundamentally mysterious. We understand some things. We understand electromagnetic interactions. We understand how light works. We understand how atoms bond together. We understand the weak nuclear force which is responsible for radioactive decay. We understand the strong nuclear force which holds nuclei together. We've gathered these understandings together in what we call the standard model of particle physics. It's remarkably successful. In many domains, it makes predictions accurate to better than 1 part in a billion. It's one of the most successful theories in the history of science. But gravity sits apart from this framework. When you try to apply quantum field theory techniques to gravity, you get infinities. You get nonsensical answers. The theory breaks down. And I think that's not an accident. I think it's telling us that gravity is the key that unlocks the next level of understanding. Gravity is pointing the way forward. When we finally understand gravity, when we figure out how to reconcile it with quantum mechanics, when we explain dark energy, when we resolve the information paradox, when we understand the nature of time, I believe we'll discover that the universe is even stranger, even more wonderful, and even more connected than we currently imagine. We might discover that space-time is not fundamental but emergent. We might find that the universe is infinite dimensional, or that it has some other structure we haven't conceived of. We might learn that quantum entanglement, which seems so spooky and distant from gravity, is actually the mechanism that creates space-time itself. Entanglement might be the fundamental reality, and space-time might be derivative. We might discover that what we call the laws of physics are not laws at all, but regularities that emerge from something more fundamental. Perhaps from pure mathematics, perhaps from quantum information, perhaps from something we don't have a name for yet. And in the process of understanding gravity, we might break down the last barriers that prevent us from saying we truly understand the universe. Not in the sense of understanding every detail. That's impossible. The universe is too vast, too complex. Every time we explain one thing, we discover that it depends on something else. That's the nature of science. But we could arrive at understanding the deep principles, the fundamental architecture, the basic rules from which everything else emerges. That's the promise of understanding gravity. That's what it means to allow gravity to break the universe in the sense of breaking through to a new level of understanding. And that's what I find absolutely breathtaking about the future of physics. Because here's the thing, you are made of atoms forged in the cores of stars. Those atoms exist because of gravity. Those stars collapsed under gravity. They burned because gravity maintained the pressures and temperatures in their cores, allowing nuclear fusion to occur. And even now, you're being pulled toward the center of the Earth by gravitational force. Gravity created you, gravity sustains you, and gravity will eventually reclaim you when you return to dust. And yet, despite the fact that gravity has shaped your existence at every moment of your life, we don't truly understand what it is. That's humbling. It's also inspiring, because it means that one of the great unsolved mysteries of science, one of the deepest questions about the nature of reality, remains open. It means that there's still frontier territory. There's still something to discover. There's still mystery left in the universe. And somewhere, right now, a physicist or a mathematician or someone we haven't discovered yet might be working on the insight that transforms everything. That insight might come from a completely unexpected direction. It might require thinking about gravity in a way nobody has thought about it before. It might come from combining ideas from quantum information theory with ideas from cosmology. It might come from a child doodling in a notebook. But when we finally solve the mystery of gravity, the universe will never look the same again. This is COSM Hush, and this has been our exploration of the main mystery of gravity. How it might allow us to break the universe, to transcend our current understanding and reach toward a deeper truth about existence itself. We've explored Newton's gravity and Einstein's revolution. We've confronted the contradiction between quantum mechanics and general relativity. We've grappled with dark energy and the cosmological constant problem. We've considered black hole information paradoxes. We've imagined space-time emerging from quantum entanglement. We've asked fundamental questions about time and the arrow of time. And we've glimpsed the possibility that gravity might be emergent, not fundamental. The journey continues, the mystery deepens, and the greatest discoveries in physics are probably still ahead of us. They're waiting to be found by the next generation of physicists, the next generation of scientists, the next generation of curious humans who look up at the night sky and wonder about the nature of existence. Thank you for joining me on this cosmic journey. Thank you for thinking deeply about these profound mysteries. Thank you for wondering, because that's what makes us human. That's what makes us scientists. That's what drives us forward. Keep looking up, keep wondering, and keep questioning everything. Because that's the spirit that has driven human understanding forward. And it's the spirit that will eventually solve the greatest mysteries of all. Right now, as you are reading these words, as you are breathing, as the earth turns silently beneath your feet at 1,000 miles per hour, something is falling toward you. Not a meteor, not a comet, not some ancient rock from the outer edges of the solar system that wandered too close. Something we built, something we launched, something that spent 14 years doing arguably the most important scientific work any spacecraft has ever done in near-Earth space. And now, its job complete, its fuel exhausted, its batteries slowly dying in the cold vacuum beyond the atmosphere, it is coming home. Its name is Van Allen Probe A. It weighs approximately 600 kilograms. That's roughly the weight of a full-grown brown bear, or a vintage Harley-Davidson motorcycle, or about 4.5 washing machines bolted together and hurtling through the upper atmosphere at 17,000 miles per hour. And somewhere over the next several hours, it is going to hit the atmosphere. Let that land for a moment. We are not talking about some abstract astronomical event that happens millions of light years away, something you need a telescope to appreciate. We are talking about a piece of American engineering, designed by American scientists, built by American hands, paid for by American taxpayers, launched from American soil, completing its final arc and returning in the most dramatic fashion imaginable to the planet that sent it skyward. This is the story of Van Allen Probe A, and it is one of the most fascinating stories in the history of American space science. But to understand why this moment matters, why this particular piece of hardware deserves more than a footnote in tomorrow's news cycle, you have to go back. You have to go back to the beginning of the space age, to a time when humanity first dared to look beyond the thin shell of air that protects us from the lethal fury of the cosmos. You have to go back to a discovery so surprising, so fundamentally important, so completely unexpected that it changed everything we thought we knew about our own backyard in space. You have to go back to 1958. January 31st, 1958. The United States is in a state of barely contained panic. 4 months earlier, on October 4th, 1957, the Soviet Union had launched Sputnik, a 184-pound metal sphere about the size of a beach ball, into orbit around the Earth. The beeps it transmitted back to Earth were picked up by ham radio operators across America, and those beeps hit the American psyche like a psychological thermonuclear device. The Soviets were in space. The Soviets were orbiting the Earth. The Soviets, who had tested their first nuclear bomb less than a decade earlier, who had built an intercontinental ballistic missile capable of delivering a nuclear warhead to American soil, had now demonstrated that they could put hardware into orbit, which meant, by extension, that they could put nuclear warheads into orbit. America's response was the kind of frantic, urgent, borderline chaotic mobilization that only happens when a nation feels genuinely threatened. The Naval Research Laboratory had been working on a satellite project called Vanguard. But Vanguard was moving slowly, carefully, methodically, the way good engineering moves when it isn't being rushed by geopolitical terror. Then Sputnik flew, and suddenly Vanguard was the most important project in America. And then, on December 6, 1957, in front of a live television audience, Vanguard's rocket rose about 4 feet off the launch pad and exploded. The satellite, a tiny 3-pound sphere, was thrown clear of the explosion, still transmitting, lying in the burning wreckage at the base of the launch pad. The press called it Flopnik. The humiliation was complete. America needed a win, and America needed it fast. The Army Ballistic Missile Agency, led by Wernher von Braun, a complicated man with a complicated history who had built rockets for Nazi Germany and was now building them for the United States, had a rocket ready. The Jupiter C. They had wanted to launch a satellite since 1956 and had been told to wait while Vanguard took its shot. Now, with Vanguard burning on the launch pad, they were given the green light. They had 90 days to do it. They did it in '84. On January 31st, 1958, Explorer 1 lifted off from Cape Canaveral, Florida, and became the first American satellite in orbit. The scientists, engineers, and technicians who had built it, many of them barely sleeping, running on coffee and adrenaline and the particular kind of focus mania that descends on people who know that history is watching, stood in a room in Washington and waited. And waited. The satellite was supposed to make contact at a specific time, when its orbit brought it over receiving stations. The time came. Nothing. The time passed. Still nothing. The room was silent in the particular way that rooms get silent when everyone in them is trying to hold on to hope with their fingernails. And then, 25 minutes late, the signal came through. Explorer 1 was in orbit. The first American satellite was in space. The men in that room embraced and wept and held each other up. But something was wrong. Not with the satellite. The satellite was fine. The problem was with the data. Explorer 1 carried a Geiger counter, a device designed to measure cosmic radiation. The scientist responsible for that instrument was a man named James Van Allen, a physicist from the University of Iowa who had spent years studying cosmic rays by attaching instruments to high-altitude balloons and rockets. He had been arguing for years that the United States needed to study the radiation environment near Earth from orbit, and he had finally gotten his chance. The Geiger counter worked. It transmitted data back to Earth. But the data was strange. At certain altitudes and certain positions in the orbit, the radiation readings went through the roof. And then, at other points, the Geiger counter went completely silent. Not low readings. 0 readings. As if there was nothing there at all. Van Allen and his team puzzled over this. A Geiger counter doesn't just stop working. If there's nothing there, it reads nothing. But if there's something there, a lot of something, if the radiation intensity is so high that it saturates the detector and overwhelms its ability to count individual particles, the counter goes to zero. The silence wasn't absence. The silence was an overload. Van Allen ran the math. He ran it again. He ran it a third time and then called in his colleagues to run it with fresh eyes. The conclusion was inescapable. Surrounding the Earth, at altitudes ranging from roughly 1,000 kilometers to tens of thousands of kilometers above the surface, there were zones of intense, trapped radiation. Belts of high-energy charged particles, electrons and protons, trapped by the Earth's magnetic field, spiraling back and forth from pole to pole, bouncing like cosmic pinballs in a vast invisible cage made of magnetism. No one had predicted this. No one had imagined it. The textbooks did not contain these zones. They did not exist in any theoretical framework that anyone had developed before Explorer 1 flew. They were real. They were massive. They were everywhere in a cosmic sense. And they were entirely unknown until a physicist from Iowa, working with a satellite that almost didn't get launched, discovered them by accident. We named them after him, the Van Allen radiation belts. The Van Allen radiation belts are, by any measure, one of the most extraordinary features of our immediate cosmic neighborhood, and one of the least appreciated. Ask the average person what lies between the surface of the Earth and the Moon, and they will probably say space. Just space. Empty, dark, cold space. They're not entirely wrong, but they're missing something crucial. What actually lies between you and the Moon is a seething, dynamic, constantly shifting environment of charged particles and magnetic fields that is as complex and as violent, in its own way, as anything you'll find anywhere else in the solar system. It is a place where electrons travel at close to the speed of light, where protons carry enough energy to penetrate the walls of a spacecraft, where the radiation levels in the heart of the belts are high enough to kill an unshielded human being in a matter of minutes and damage sophisticated electronics in hours. It is, in the very technical language of space science, a seriously hostile place. And yet it's right here. It's not around Jupiter or Saturn. It's not in some distant region of the galaxy. It's right above our heads, starting at about 1,000 kilometers altitude and extending out to about 60,000 kilometers, well past the orbit of the Moon in terms of the inner edge of the magnetosphere's influence. The inner Van Allen belt is the more stable of the two. It sits roughly between 1,000 and 5,000 kilometers above the surface and is dominated by high-energy protons,